Let's see. Are we live? Let's wait for the preview. Alrighty, we're live. Perfect. Okay, so welcome everyone to another stream on stuff that I do. So, last couple of streams we've been working on one of my robots, but we're completely shifting gears today. We are going to be addressing a project that I've had on the back burner for most of the year. One of those, let me buy parts for it and then completely forget about, or well, buy parts for it and then it, sit in the back of my mind, nagging at me that I haven't finished it yet. So today, hopefully we are going to start making some progress towards that goal. And that goal is that I want to build a new NAS. Specifically, I would like to build a rack-mountable NAS because I bought one of those GeekPi 8U 10-inch racks. And I want to be, the biggest feature for me anyway, is that I'm going to be upgrading the compute that's inside of it. My existing NAS is based around a Supermicro, I think it's called an X10, or it's called a something X10 SDV or something. I think it's a Xeon D based system, which is a quad-core, low-frequency Broadwell core from way back when. But the cool thing about it was quad-core Xeon. It had ECC memory. It had integrated IPMI. So all those nice servery features that that you've come to expect, that you expect from a server board. Integrated A-speed IPMI, a bunch of other niceties. So it also has a lot of onboard PCIe. It had 2 onboard PCIe Gen 3x4 M.2 slots, and it also had a X16 Gen 3 slot that was fully bifurcatable. So it also had 6 onboard SATA ports. So what my current NAS has is basically it has a boot drive, or the other big feature of the Xeon D is it had dual integrated 10 gigabit NICs on the SoC. So you didn't have to put in a external network card. So in addition to those 2 10 gigi ports that come off the CPU, I had a boot drive that was a M.2, just a small low power M.2 disk for the boot volume. It has 2 ZFS metadata special small blocks disks installed in RAID, mirrored, and then it had 6 HDDs plugged into, let me rephrase it. Sorry, the board had. It has 1 onboard M.2. I'm sorry. So my boot drive is in the onboard M.2 Gen 3x4 slot, and then I have a basically a port multiplier, not a port multiplier, a X16 card that gives you 4 M.2 slots, but requires your board to support bifurcation, which this board does. So in the system, I have a boot volume, 2 cache volumes, 2 cache volume / metadata small blocks drives, and then that covers most of the PCIe, and then the 10 gig is integrated, and then it had 6 SATA large hard drives plugged into it, and the performance of it is completely fine by the standards of what I need. So we're not really necessarily looking to upgrade the speed of anything right now, of the storage. But what we are looking to do is upgrade the host CPU, because I would like to run services on it. One of them being Jellyfin for my Blu-ray RIP collection / home media collection that I've built up of my robotics videos for years. It's so on and so forth. So I'd like to run Jellyfin, and while the Broadwell CPU can keep up with just me watching it, which is really all I need. As far as transcode goes, 4K video, it eats the entire 100% of the CPU, can't do anything else. So if there's any other services running on the system, you completely tank it. So I wanted a lot more power, and to that end, what I purchased is a board called a Minisforum. I believe it's a BD790i. So it's a mini-ITX system. This is a power supply, DC-DC supply that I have hanging off of it. It is a 16-core laptop CPU, or laptop CPU. Low power, I think it pulls like up to 55 or 75 watts. It takes 2 SODIMM DDR5 memory modules, so I got 96 gig installed in it. It's got, it only has, I believe, it might have 2.5 gig E. I'm not sure. It might even only be 1 gigabit. But what we're going to do is we have a lot more expansion options in this, or not that many more expansion options. So there are 2 M.2 slots on the motherboard under this heatsink right here on the top. And then there is an X16 slot, and these are all PCIe Gen 5 slots, which is really nice. And so what we're doing, and so the so we got that. So you'll notice that there was no onboard SATA. I don't actually think that. Yeah, I don't think there's any onboard SATA. So got a bit of a problem there if we want to put hard drives in it. And to that end, I have a. Actually, I'll turn on the desk cam for this in just a second before I start throwing hardware around. So the goal, anyway, I have a. Let me put this down. So we're going to try to fit this. I have a M.2 SATA controller. I have a low profile 10 gig dual 10 gig E NIC, and then I have this fun expansion card that is going to make some people scream in horror, to be honest. But so we've got, so what this will do, this magical, horrible, wonderful thing, is another one of those type of bifurcation cards. Except what it'll do is it gives you 2 M.2 slots, one on either side, and those take up each 4, but in total 8 of the lanes, and then the other 8 lanes are brought out to the top connector. So you basically cut the slot in half up to whatever's plugged into the top, and then it gives you 2 additional M.2 devices. So, I mean, one of the things I want to do is figure out how to move these little cards. Oh, I see how I'm supposed to do it. Okay. Where was I going with this? Right. Fun. Right. Okay. So got this. So a lot more random, again, a lot more random hardware to plug into this, and that's the difference between your server boards and your consumer boards. And the one last thing, anyway, is I purchased, and I did receive it before the tariffs screwed me over. I purchased a JetKVM, which is a generally well-approved IKVM module that lets me log into, essentially, it captures the HDMI off the backside, has a connector interface that plugs into this, well, you'll see, it plugs in, or well, I don't want to pull this out, but plugs into this board, which plugs into all of the onboard switches, connectors, inputs, stuff like that. So with all of this random stuff, I can match the onboard functionality of the old board. But the thing is, the CPU is so much faster, it's not even worth trying to make a comparison between the two. So yeah, so let me pull, so what we're doing today is we're going to start doing some 3D modeling of this enclosure, and probably the most complicated component of the whole thing, ironically, is finding out the freaking specifications for where to put the mounting holes and where to put the expansion slot connectors. Because while it's really easy to find how the motherboard hole spacing is, in terms of finding definitions of where the I/O expansion cards are, or the back slots are relative to the motherboard, is actually really not well defined. So I found this really helpful post on overclock.net from a user called Gertie. I'm assuming that's how that's pronounced. Gertie. Either way. So he or she, they go through, basically went through all the different specifications, and then from all of it reverse engineered what the whole thing should look like from a spacing perspective. This is essentially viewed if you're sitting at the front of the case looking backwards, or if you're sitting at the front of the case looking through it at the back I/O cover. This is what it's supposed to look like. So we're going to be referencing this a lot today, and we're also going to be referencing the mini-ITX specification. I think this is the 2009 one, but the layout hasn't changed in terms of the board hole spacing. So we'll be referencing this quite a bit. So we're going to be doing, because I love using free software when I can. I'm not married to it, but I do run Linux, so that kind of limits the software available to me sometimes. But we're going to be doing this in FreeCAD. So this might also serve as a what can I do with FreeCAD, although we're making lots of squares, nothing too complicated. So yeah, so let's start with this. And so I think a good point to start at is I want to print the most minimal amount of stuff to verify that I've placed things in the right spots. So considering the only major question is where the I/O slots are being placed, I think that that's where we ought to start. So we're going to essentially make a 3D model that covers just the lower parts of the screws, and then where I would plug in the PCI expansion card just to verify that all of my alignment is correct. The other thing, before we get just into that, let's kind of figure out the layout that we want in the rack. So let me put some of this stuff down. We also have since the last time, we have the two beautiful little kittens that I adopted. They're mine. They're not Foster's. They are mine. And all right, so we've got our mini-ITX board. I'm going to turn on the desk cam here in a second. Got to figure out how we want to lay out things in the enclosure. So let's spin around and look at the desk cam, which is just a phone on a really cheap, at least it's not AliExpress mount, but it's Amazon Basics, so same difference. So desk cam, turn on the light. Let me look at my horribly grimy keyboard. Sorry about that. Make sure I've got it generally aligned. I'll just open the keyboard here, just to give us a little bit more operating space. Get the cat hair off my desk. Alrighty, so. Oh, right, that's not bolted down. Okay, so we have got this rack here. Yeah, so. Alright. So, they have a little bracket up here for mounting like some kinds of boards. So, let's look down and not point it at my crotch. Here. So, we'll just use this tray as kind of just a simple concept here for a second, just basic alignment. So what we want to do is we're going to figure out kind of how we want to lay out pieces of this. So, I'm thinking that what we're going to treat the part that's currently on the table as the back of the board. So we would want, my thought, because we get to put all these drives on the top, conceptually, what we're going to do is I'm going to try to keep the board slid over as much as possible, just to try to keep the expansion card out of the way. So we're going to hopefully have the board as far to the one end as possible, just to try to keep the expansion card on the side of the vertical volume, because my hope is to have a 2x3 arrangement of drives in here. So essentially there'll be 2 wide, 3 tall, and I'm hoping to fit the 6 drives into 2U of rack space. Because with a 3.5-inch drive, 2 of them sitting next to each other, 7 inches, give them an inch of spacing just for hardware, just for airflow at whatever 6. So let's say 8 inches. So that only gives you 2 inches of width on the rack. So we want the network card squished over to the side as far as possible. So the idea is that we would put the motherboard here. The hard drives would be aligned to one side, and then on this side we'd have our vertical bit for the network card. And then if there's enough vertical space or enough empty space on the panel, we'll give ourselves a place to squish in the JetKVM to have a JetKVM front panel. So again, we're going to have hard drives basically offset to the right a little bit. I mean, if we could put them centered, that'd be cool too. I just don't know if we'd have space. And then we're going to have to figure out how to bolt this power supply in here. I think we can fit this all into 2U. Yeah, it looks like it'll fit. If not, we'll figure it out. Yeah, we'll figure it out. And then, yeah, I think that's how. So then the big question, the first big question, you know, the one where I said, you know, the actual alignment of the slots, we need to figure out how much height I need under the board, because that's one thing that's not answered in here is, you know, how big do the standoffs need to be under the motherboard? And then does that give us enough space to, I don't know what I'm saying, enough space to, because we gotta account for the taper of the expansion slot here. I don't know if we need to cut the hole wider than, yeah, you'll see. So we're just going to take this. We're going to insert the network card in. Remember, this is X8, so we're not losing anything by having this slot length. I'm going to plug that in here. And basically we can see that, luckily for us anyway, that the if you look at the back here, pretty much the board, and again, this is, you know, all nice, happy things part of the standard, is that the taper starts basically at the same point as where the bottom of the PCB is. So if it's kind of hard to see here precisely, but pretty much the bottom of the taper is aligned, or the beginning of the taper at the wide part is aligned with the bottom side of the motherboard, the bottom side of the PCB. So we can account for that. So, and even if we go back to the drawings, we can even see that that's noted here. Basically, the taper starts. Okay, well, I mean, it notes at the top of the motherboard, but, you know, I could have the card kind of, yeah, kind of had the card rocked a little bit. So, I mean, it's 1 millimeter, so it's probably not too much of a thing to worry about. But spec-wise, it's probably closer to this than what I can see here. All right, bring this back up. Come on, switch. There we go. All right, so let's just give that a good old measure. And to be honest, this motherboard has the BIOS battery like plugged in via a header on the bottom, so we probably should just check the height of that rather than the absolute minimum of the, consider that our minimum standoff height. So let me just put that down. Grab my calipers. All right. And then measure the clearance that we need. That's probably going to be 0. No. All right, 0 the calipers. Measure on the bottom of the PCB, or not the bottom of the PCB, the bottom of the battery. We got with a Mark 1 eyeball here on the alignment, just giving ourselves a little bit of extra space. Looks like we got about 5.5 millimeters of vertical clearance that we're going to need to handle this battery being down here, which is perfectly fine because the same level of clearance is, if we go over here, easily gives us what we need. So yeah, if we see here, this is the under the battery, and that gives easily the vertical distance we need here. I don't know if there's a standard on what the motherboard's standoff average is. We'll look that up in just a second. But yeah, clearly fine on the vertical. So we only need to account for the bottom bit of the connector here. So let me just unplug this, and just to give you an idea of what it looks like with this hilarious expansion card thing. Just pull that back out here. Kind of give an idea of what these will look like when they're assembled, right? And so kind of clip together like this, and effectively it turns into a full height card. So we'll need to be making ourselves a bit of a custom bracket for this, because I don't have a low profile bracket for this, and I mean, I want to hook onto the bottom of this too, just for stability's sake. I mean, this feels super jank, but that is what we do around here. So, yeah, all right, cool. And perfect. What are we going to do here? Right, let me just put this away before I lose something. All right, so step one is going to be printing just a test jig of bolt into these two holes on the bottom side and then have the little gap for the card edge vertical bracket, just to verify that we've done everything correctly. All right, so let me just put some of this back down, put this thing back where it came from, and then get into the modeling software. That over there. All right, I guess I just ought to show the little SATA expander here before we put all this stuff away for a bit. Alrighty, so yeah, that's what this looks like. It's 6 SATA ports as an M.2 device. I think it's only got 2 lanes, so max data rate's probably like 1.6 gigabytes per second. But let's be honest, a spinning hard drive operates at what? 200, 250 megabytes a second on a good day. I got 6 of them. That's 1.5 gigabytes per second. 1.5 gigabytes per second PCIe link. Yeah, we're fine. I mean, if you were trying to do SATA SSDs, obviously more of a problem. But if you're doing SATA SSDs, just get a flash store and be happy. Don't worry about any of this. The interface bottleneck is not a problem as you might think it is. It's only got tool 10 gig E. Like, you're not going to be able to egress data fast enough anyway. Okay, let me put the stuffy stuff back on the ground so I don't short anything out on wood. Okay. Alrighty, cool beans. Alright, cool. Switch back to the desktop. Alright. So, 5.5 millimeters we measured. Remember that number. I won't. I mean, I will, but I won't. Alright. Pull my keyboard back in. Alright. Turn off the phone. Turn off the light. Spin this out of the way. Alrighty. Alright. So, first thing is first. Again, if anyone is watching, just leave a comment if you have any questions. Alright. We'll do new project. We're going to save this as NAS Enclosure, NAS parts. Why not? NAS parts.freecad. So we're going to say new part. This is going to be test expansion bracket test jig. Just forget the jig part. We'll just expansion bracket test. We're gonna make a body and name that as expansion bracket test body. And actually, this is a expansion slot placement test, not bracket slot placement. Alright, and so let's start with a sketch. Put it on the XY plane. And then we're going to define a rectangle. No, we want a centered rectangle. Oop. And then what we're going to do is we've got two hole. Hole spacing here is 6.1 inches. Or 154.94 millimeters. So we're going to do this. We're going to do this. These are going to be standoffs. So we're going to define a distance between these of 154.94 millimeters, and that's going to be large. And we need to expand that. What we're going to do here, define this as, I'll just call this, because the motherboard is, I think it's 170 millimeters, right? Is the definition of a mini-ITX. So we're just gonna give ourselves a test width of 40 mil here. We're gonna define a spacing. Well, what we'll do is we'll define the expansion slot bit up here. Oh, damn it! I'm sorry. Define the expansion slot as a thing that pops up here. We're just going to define our 40 mil test here. So these will be standoffs. So what we're going to do, so we got the spacing, and we'll just make sure that these are equidistant from each other. So we're going to define just 154.94 divided by 2. There's probably a much better way of doing that. I know there is. Okay, so standoff. We're going to make sure to use, actually, what is... PC mother, actually, it told me right here, what's the hole diameter? It's 4 mil, or it's 3.96 millimeter hole, so that's just a bit smaller than an M4 bolt. So we're just going to assume, an M3 bolt, like that. That's probably the best thing to do. Here, hold on. All right, so we're gonna, datum 00 is hole C. Interesting. Okay. Sorry. Yeah. So 3.96 mil hole, 4 by 0.16 inch. Right. Okay. So yeah, 3.96 mil hole. We're going to use a M3 bolt. I've got some threaded standoffs, so. Those need a 5 mil hole, so just to give ourselves millimeter. Mil is different in the US. That's thousandth of an inch, which is stupid. But either way, so if we need a 5 millimeter hole in order to place our threaded insert, let's say we want 2 millimeters of clearance around that. So that's 5 plus 2 plus 2. That's 9. So we'll define our things here as actually, sorry. We'll define. We have to define these later. I'm sorry. Cool. This is our test. We're going to do because it's 3D print, we're going to do a padding of, we'll call it 4 millimeters thick. It's probably a lot. That's probably a lot. We really probably, it's just, I don't want this thing to flex on us, but 3 millimeters is pretty darn thick for or 4 millimeters pretty darn thick. So we'll use 3 millimeters and see how flimsy stuff comes out. All right, so now that we got this, we're going to go on top here, do another sketch. Now we'll put our standoff placement. Sorry, these are going to be 9 mil holes. We're going to have a spacing of, all right, we're going to do 154.94 divided by 2. Divided by 2. We're going to define that these are vertically aligned, and then the distance from center, we're going to define this as, well, actually, we need to figure out what the definition of this is. So, yeah, because these are not placed here, but we got to figure it out. So what we're going to do is we're going to define essentially this line is the back side of where this expansion connector goes. So what we'll do, so let's go to this drawing guide here, and from, let's see what they do. So they say, so from the edge of the mini-ITX board, 7.92 millimeters to the middle of the slot. Because I believe down here we're going to define the position of the expansion. Actually, no, I take that back. We're going to define the position of the opening relative to the PCB inside the slot. Oh, Christ. Hold on, processing. All right, so we define the size of the hole and the position relative to the top of the PCB, which is fine. We now need to figure out the distance of the PCB from... Well, actually, I mean, if it's the PCB, we know how thick the PCB is. We know... oh, jeez. Okay, we're gonna use the spreadsheet tool in here. Let's just figure that out. We're gonna say we're gonna close a sketch. We're gonna go to the spreadsheet tool so we can do some math. We're gonna rename this to parameters. We're going to say board edge to PCIe slot center. All right. Copy that, take this, place that as the alias. And we saw down here that the distance from the board edge to the center of the connector is 7.92 millimeters. 7.92 millimeter. All right. And then we're going to say PCIe card thickness, and that is 1.57 millimeters, I believe, defined by this. It's 1.6 really, but you know, I did 1.57. You know, I think is the actual. If you measure some PCBs, I think they're closer to 1.57 than 1.6, but you need some good tools to measure that. Right. So, all right. So we got our board edge to that, and then we need board edge to mounting hole. We're going to pull that out of our mini-ITX specification. And so we can see that on the lower side here, we need... okay, so we actually need to... Okay, we did that wrong. Sorry. What we did wrong is these holes are not centered on the board. They're slightly offset. So even though, yes, the board is 170 millimeters wide, right? Yeah, 170 millimeters wide. The hole placement is not square. So we can fix that. So what we'll do here is we know that they are at least vertical of each other, but we need to go in... Ooh. Something funkied out. Sketch. All right, we built our PCB thing, and actually, yeah. So we're gonna say that this is fully under the PCB. So we need to change that. Actually, again, define parameters. One row above, we've got lower mounting hole spacing. I see. These have names. Yeah, we'll use these names up here. So we'll say mounting hole CH spacing is going to be C to H, so this vertical one, is 154.94 millimeters. So 154.94 millimeters. We'll copy that. Alias, and then do one row above. We're going to be C2 edge. Okay, we're going to do the mount, or actually, sorry, we don't need lower mount. We just need board hole CH spacing. So copy that, change the alias name. Okay, and then we're gonna get board hole C lower edge spacing is 0.25 inches or 6.35 millimeters. And then the same thing for, are these all going to be the same edge to edge spacing? So like it's 0.25 here. What is this to edge? Is it the same? Is it different? I don't know. I mean, we can compute this, right? So we know 0.25, 6.2. I mean, 170 millimeter. Oh, it's calculated in millimeter. Fine. It's just I wish the whole. Clearly, whoever designed this, the whole spacing is in inches, is in at least a 2-digit, inches, and then the overall size is in millimeters. Like somebody was smoking something, I swear. So yeah. So either way, 157 plus 6.35. Wait, no, hold on. Yeah, so 157 plus 6 is 163. 160. Almost 164-ish, so plus another 6. Yeah, so this vertical board, so all of this, I don't even know what the one down here is, 0.4 plus, or 10, so 1, yeah, so 160, so plus that 164 point, yeah, almost. Dang, this is a little annoying. Wait for... Well, we can compute it anyway, just shenanigans. Okay, so... E2C. No, this is this inset too. Okay, I'm complaining more than I actually am annoyed, so that's just me being silly. Okay, so we've got 0.25 here. 8. All right, so yeah, C to H is that, and then we got you know the way this is? I think these are almost going to be square with each other. So let's try this. So Python. If we do 157.48 plus 6.35, and we do 170 minus that quantity, it's basically 6.1. It's almost the same. I bet they intended to make it the same. So like if we do 6.17 millimeters times 25 point, divided by 25.4 millimeters an inch, like it's 0.24. Like it's 1/100th of an inch off. Some people are screaming for mixing up my units, but these are the more square units. I'm sorry. Like I'm fairly certain they intended this to also be like 0.25. So like 6.2 plus 2 or plus 0.5. So both of these added together. So I bet it was intended to be a 6.7 inch, board thereabouts. We defined it as 170 millimeters because it's easier. Like if we did 6.7 times inches times 25.4, that's millimeters an inch. Yeah, 170.18 millimeters. Like it's 0.2 millimeter off. It's the one layer line on our printer. Across the whole width. I'm pretty sure they were intending them to be the same. Yeah, so, and then vertically, we've got, 6.1 plus 0.4, so that'd be, 6.5, maybe 6.75 coming the other way, which, is more, so, maybe, well, we'll go with the millimeter specifications. I hate mixed units. I'm going to be using mixed units. I hate mixed units. I'm sorry. All right. So, C to H spacing, 154.9. Actually, let's let KiCad do the FreeCAD do the conversion. So we're going to actually say 6.1 inches, which is 100. Okay. And then we're going to say C to H spacing, actually, one row above. Board, hole, C, I think it's A, right? That's F, CF, C inset. That's going to be, you know, O equals 0.4 inches. C to H spacing, and C, I'm gonna say lower left left spacing. Where's mounting? Yeah, board left spacing is going to be 0.25. That's going to be board edge to mounting hole. Yeah, so that's our handy dandy 0.25 number. So we can actually delete this row. And then we're going to say board hole CA inset. And that is, you know, 0.9 inches. Then we can say one row above, and then board hole right spacing. I'm going to say board width is 170 millimeter. Height is 170 millimeter. All right, so board right spacing is going to be equal to board width minus board hole C CF spacing. I didn't define CF spacing, sorry. That's CF inset. Is going to be equal to 6.2 inches, because we hate everything CF spacing. Right, so board hole, sorry, so yeah. This is going to be board width minus board hole CF spacing plus board left, board hole left spacing. Cool, and we've cleared the errors. Nice. Okay, so then right spacing. So we've computed that, right spacing, and then bottom spacing. Bottom, we'll just call that inset, because we've been using spacing for the horizontals and inset for the verticals. So board hole bottom inset is going to be board height minus board hole C inset plus board hole CH spacing. Yeah, 4.9 mil. That's quite a bit less, yeah. Bottom inset. Okay, now that we've defined all of our parameters, Thank you. All right. LabVIEW got a UI update. Yeah, I guess it did. There's a joke there. I told this guy back in college that when I first met him, he's like, "What do you think of LabVIEW?" And I was like, "LabVIEW sucks." And that was my first interaction with Totalizer. Forever remembers that, and I forever remember that too. So yeah, but Hassan, the reason we're doing this is just to try to quantify some of these data sheets, some of these specification numbers into our design, because this is going to let us, one of the cool things about FreeCAD is that you can, when you're defining constraints, you can use parameters out of your spreadsheet. So you can take a spreadsheet, punch in numbers, do math on those numbers in the spreadsheet, and then copy those, have them drive variables in your design. And you can even then go back to the spreadsheet, update a value, and it will recompute your model for you. So they call it a parametric modeler. I would be shocked if like Fusion 360 or SolidWorks doesn't do this too. It's just I've never used those. So yeah. So I got this. We've got something funky happened. There we go. Right. Bringing back the renderer. All right. So we're going to define everything relative to we're defining this top bit of this extrusion here as essentially the top of the board. So what we'll do here, rather than doing these spacing parameters, so we're going to do an overall spacing between these two. And now what we can do is parameters dot board hole CF CH spacing, yeah, because the reason it's CH is so these holes right here, so up here we define basically this is a hole C, this is hole H, then we've got hole F, and then hole J. So I think I actually named some of these wrong. So yeah, so CH spacing was supposed to be the vertical one, and then we got CF spacing is the other one. I think I might have left some of these called CA. Yeah, so this is CF inset, sorry. And then the vertical one here, I think I didn't define. Oh, right, I forgot to define. Anywho, we're good here. So yes, so we're gonna do. This is our. So what we're doing first here is just to test our assumptions of these numbers. Okay, so, yeah, so basically what we're trying to do here first is we're just trying to make sure that we've got all the numbers correct for basically these, since you guys joined after I think I explained it, we're trying to make sure that we've got the spacing between these expansion slots in the motherboard correct, because there's not really a good resource on, or I should say, there in the specification, there are two that you need to be aware of. There's the ATX specification for the motherboard, and then there is the PCI Chem, or CE. A lot of people call it Chem, the acronym is CEM, or Card Electromechanical Specification. And both of them define parameters that you need to know in order to figure out the overall dimensions of what a case or a mounting jig for this whole thing should look like. But the ATX spec doesn't tell you where the expansion slot holes need to be, and the PCIe specification only tells you what the back of the cards look like, and the physical size of the connector, so you have to merge the two together to figure out where the alignment for a case design needs to be. So this wonderful person on overclock.net here, a couple of years ago, posted this. He went through and he did all the math. He did the numbers and built this whole thing showing us the relevant pieces of information that you need to know in order to actually define the layout here. Thank God. I'm gonna have to print out a copy of this so nobody takes it down, or at least tell archive.org, to archive this site. But either way, so we're just trying to make sure that we got the spacing right. So particularly, the numbers we're working off of here are, we've got this number right here that tells us what the distance between the board edge and the center of the PCI Express connector is. And then we've got this other piece of information that defines what we've got then Then we got this piece of information that tells us how thick the card is, and then we've got this piece of information that tells us where the hole in the back is placed based on a distance from the board and then a width. Realistically, what we're just trying to do is we're trying to make sure that we've cut the hole. We just got the alignment right. Then we're going to turn this all into a larger case model. I just want to make sure that I'm trying to do the minimum printable object to test that I got my numbers right. At least most of them anyway. Where am I going with this? Right, so we have defined the distance between the holes that we need. We will then define the inset from the edge. So we're going to do a import external geometry, and we're going to do a distance from the center of this hole to the edge of the board, and that is going to be the parameters. That is board hole C inset. And then we're going to need, we're going to need to define, we're defining the y-axis here as essentially the bottom of, basically the y-axis here is going to be the left side of our motherboard, and the top of this piece of model here is going to be the top of our motherboard. So we're then going to define a distance between this hole and there based on the inset that we have. So this 0.25 mil, but we called it parameters left spacing. All right. And then I'm going to go turn this standoff width into a board standoff diameter. I'm going to call that, we're just saying 9 millimeters. And the reason this is 9 millimeters, I've defined this as 9 millimeters, is these holes are 3.96 millimeters, so not quite 4, which means theoretically I don't think you should be able, I don't think you can put an M4 screw through this, because M4 is defined as 4 millimeter, and I don't know if, I think it might be a little larger than 4 millimeters at the outside of the threads and a little thinner than 4 millimeters on the inside of the threads. So you can't put an M4 bolt through that. So we're going to go with M3. Because I don't think there is an M3.5. Because again, this is all 0.16. This is meant for I believe an 1/8 inch screw, or a 440, right? Is what I think your standard PC screw is. Because PC cases are just a horrible conglomeration of both imperial and metric units. Like I don't know if you were here for it earlier, but it was like the board width is defined in millimeters. The hole spacing is defined in inches. Like, what the hell? Like, who did this? But anyway. So again, right. So we're going to do our, so again, because we're going to use an M3 bolt, the heat set inserts that I have for because we're going to use an M3 bolt, the heat set inserts that I have for 3D prints for an M3 bolt are 5 millimeters in diameter. So we need a 5 millimeter hole, board standoff hole. So we'll call that 5 millimeters. And basically what we'll do here is, rather than doing this as 9, I want the board standoff hole plus 2 times 2 millimeter. I want 2 millimeters of margin. I want my thickness of my... I want the thickness of the ring around the outside of the heat set insert to be 2 millimeters thick. So we got a 5 millimeter hole. Or, well, actually, parametrically, it can be whatever we want. We just want 2 millimeters. So we're going to take the hole size, board standoff hole, plus 2 times, we're going to say the margin's 2 millimeters, how thick we want it. And that'll give us 9 millimeters. So then we can go in here and just define our hole size. As parameters standoff diameter. And we'll call this standoff diameter. Oops. And that's just barely before the edge of the board, which is perfect. Yeah, awesome. All right. So we've got our little standoffs. And what we can do now, sorry, I keep rotating this. So what we can do now, just to make the extrusion a little easier, and the number that I think y'all missed, I don't think you guys had joined when I was, it's earlier in the stream, but when I was looking at the physical layout of things. So this number's going to look like it just magically got pulled out of thin air. But I measured it. If you look at the earlier part of the stream, you don't have to seek now, but how tall the standoffs have to be on the motherboard. We figured out that, at least for my motherboard, because of a battery that's on the bottom side of it, needs to be at least 5.5 millimeters from the bottom. There's 5.5 millimeters of clearance that's needed. So we're going to say, so we're going to do one above. We're going to do board standoff height. We're going to define that as 5.5 millimeters just for now. And then a thing that I said that I'm going to do that I totally forgot to do is look up if there's a standard on how tall those standoffs need to be. So we're going to say PC motherboard standoff height. So version 2.1 of the ATX specifications states that the length of the standoffs needs to be, at least 0.25 inches, 6.4 millimeters, with their cross-sections fitting within 0.4 by 0.4, so that's 10 mil by 10 mil, square areas centered around each mounting hole. Okay, so we're defining a 9 millimeter diameter, so we're within that size, but we need to make them 6.4 millimeters tall to be within compliance. So we'll actually just change this to 6.4. We'll add a note here. My board only needs 6.4 or 5.5 millimeter. I'll just open this up, and we're gonna add a row above. We're just gonna call this notes. But spec says 6.4 mil, so we call it 6.4 mil. So TLDR, math, yes, correct, totalizer, math. Lots of math in this video. Well, actually, hopefully not too much more. But yeah, 3D modeling. We're taking all of the numbers, plug them into a spreadsheet so that hopefully we don't forget them. So now we've got this layout here. And so because we have, okay, so got this layout, we've assumed that the y-axis, honestly, I wouldn't say that I'm new to it, in the sense that I've been doing 3D modeling for 3D printing for a couple of years now, but I don't do a ton of it. So, I mean, I think everything I have ever created is sitting in this 3D modeling folder. Yeah, so I have generated in my entire time doing 3D printing, like, how many things are in this folder? Like 18 or 22 minus these folders. So 17, I guess there's some stuff in here. There's like 17 models. For me, it needs better habit. All right. Alright, so let me just close that. I was doing some other math. So we have defined the y-axis at the bottom of the board, so now we need to place just some kind of marker point for our own reference. For reference from the bottom of the board to the center of the PCIe slot. So we're going to do another... Right, so I figured I needed another PCI board, yes, so we did, why was this 7.92 mil? Oh, right, because 7.92 millimeters, that's this number. And so we want to compute to the beginning of, well, really we want to compute to the center of where the expansion slot connector needs to be. So, by the way, is FreeCAD better for project storage for enthusiasts over Fusion? I'm only going to say, well, FreeCAD is, well, free. So if you ever unsubscribe from your, I guess, what, Fusion, does Fusion 360 have a free viewer, at least? Like if somebody already has, if you've already made a model, and you're not trying to edit the model, you're just trying to look at something you did before, you can still open it, right? And view in a read-only if your license expired, right? I don't know. If yes, then I don't think it's too much of a problem to like have project storage for Fusion 360. FreeCAD though, like you do end-to-end, you're never gonna stop paying Autodesk for a license and then lose your ability to use things. Admittedly though, I am told that Fusion is still a lot easier to use. Yeah. Honestly, I've been liking the parametric CAD because if I just punched in a bunch of numbers and then needed to get back to something, or or realistically, actually, a lot of it for me is, let's say I get the numbers perfect. But in my print, sometimes the print's not quite right because or I've exceeded the capabilities of my printer. Like I need to trim a bit here, add a little bit there. I like having the spreadsheet. And one of the things that if you ever look at any files, I've got some of them up on GitHub. But like if you ever look at some of these files, one of the parameters I like to use is that I'll define like a line for what it's supposed to be, and then spec-wise what it's supposed to be, and then I'll define basically a margin parameter, and then I'll define the what is used in the that to define the dimension. So essentially, I give myself a line item for what the spec says it should be. I give myself a controllable margin parameter that I can tweak to whatever my printer can do through usually trial and error, and then basically a third line that is either you type what it's supposed to be plus margin in your line inside your constraint editor, or you compute the margin in here. It doesn't really matter. If the spreadsheets get too big, then they can be a long time to edit the spreadsheet. Anywho, so we've got this board edge to slot number. We've defined that, and then we've defined the card thickness, which is we've got that. Yeah, long live open source. So we don't need that number yet. Right. Okay. So we're gonna say, because we've got the slot and we've got the card thickness, we're gonna say board edge to PCIe card top side. That's a horrible name, but it is what it is. But I have yeehaw time. Right. You're in Central Time Zone. All right. So we got board edge to PCIe top side. So what that number will be is parameters. Sorry, not parameters. All right. I don't type parameters in here. It is board edge to PCIe slot center plus. Actually, it's going to be minus PCIe card thickness divided by 2, because we have a number that defines board edge to the center of the card, so we need to subtract half of the thickness of the card to get us to the top. So we'll divide the card by 2. Yeah. So we got that, and I forgot the equal sign. So we got 7.13 millimeter. We got that. We paste this in here for the oops, it broke something. PC board edge to PCIe slot center. That should be fine, right? Unable to set a board edge to PCIe card. Well, why can it not set? Can I set it to something smaller? No, I've used this on accident already. Oh, that's what I did. Sorry, I literally set the name cell as the alias. Sorry, yep, there we go. Now we're good. Okay, so this.
Hello, kitten. The kittens.
And then we've got. Okay, so card top side. And then we're going to compute board edge to expansion slot center. Set this as the alias. And then we're going to do, so this is, so that's going to be board edge to, or we're going to equal side, board edge to PCIe card topside minus this is going to be a sum total of 0.35 millimeters plus 12.06 divided by 2. So 12.06 millimeters divided by 2. as defined here. And that gives us 0.75 millimeters, which is an oddly square number which it's square. How square that number is makes me feel like it's correct. Like, But, all right. So, perfect. Actually, yeah. Hold on. Let me go turn the light on for a second. So, hypothetically, so if we take the board we were looking at earlier, and we plug this networking card back into it, just to see the spacing, just to do a bit of a mental check on whether this makes sense or not. And in fact, if we look at it just a bit, I'm going to try to get this real close to the camera. The expansion connector, it's kind of hard to see, but it is just barely inset, but it is a little bit. So I find this believable. So a millimeter's not a whole hell of a lot, but it is something. Okay, so just to visualize, how much is 0.75 millimeters? I'm going to take our calipers here. We're going to dial this into 0.75 millimeters. Not a heck of a lot. Really not a heck of a lot. Honestly, I felt like it might have been a little more inset than that, but that's fine. We'll fix it if it's wrong. That's why we're doing a test first. All right, see ya, son. Thanks for stopping by. If you want to contribute to what the next stream topic will be, there's a poll on my post list. Try to figure out. I want to do another robot project, but I just don't know what people want to see, because me hacking on a robot I already built is less interesting than starting something in stream that everything can be followed. But either way, thanks for stopping by. So, let's see here. Whoever is left, thank you for watching. We've got this definition here, board edge to expand to slot connector. So let's now define, so that we've got this bit defined. So we're just going to put the holes in so we can make these standoffs. So we're going to define a new hole. This diameter is going to be, hold on, what was my constraint tool here? I think it was dimension. Just D, sorry. Dimension, this is going to be parameters, hole size, or standoff hole size, or, yeah, it's standoff hole. So we'll do that, and then we're going to put another circle in here. We're going to do a constraint, define that, put it in there, and then we can save that. We can then do an extrusion. If we go back to the part design, we'll do a pad. We'll call that parameters standoff height. All right. And then what we shall do is on the top here, we're going to define another sketch. Then we're going to pull in some external geometry. We're going to do a rectangle. Oh, this, not a centered rectangle, just a rectangle. Rectangle. This is going to be coincident point. These points are going to be coincident. We're going to define this as, well, realistically, this will be the, just represent the back. Actually, I did this wrong. Sorry. Parameters. Oh, sorry. All right. Actually need 2 rectangles, one over here, one over here. This will be coincident. This will be coincident. These will be horizontal of each other. We're then going to define a point that is also horizontal with these, and then we're going to define a, this point's going to be over here, because what we need to do is define a, this is our board edge, our PCIe slot. Oh, no, that's not right. Board edge to PCIe expansion slot center. Probably should change the name on that. PCIe bracket center. We'll call it that. PCIe bracket center. Gotta change this because this is now no longer a thing. Bracket center. Okay. Alright, so then what we're going to do is typically, I mean, this define, or actually, so the width of one of these card edges is officially defined as 10.19 millimeters. So, yeah, 10.19 millimeters. So let me, again, get a real card here and measure. Spec says 10.19 mil. See what a real card actually is. Real card, so I take calipers, measure it. Let me just make sure the calipers are zeroed. Measure this. Yeah, the real one is 10.26, even though the spec says 10.19. So what so usually you'll add like 1 or 2 millimeters to this. So we're just gonna say 12 to give us a millimeter on each side. Yeah, that looks good. So we're just gonna say so we're gonna say parameters, PCIe, or actually no, we'll just type this in just for now. So we've got this. It doesn't really define a length of this bracket, so we're gonna do that out. How thick is this metal? It's 1 millimeter thick. So yeah, we'll just say 1.2 just to give ourselves some margin. So so to say PCIe bracket thickness, and that'll be, we'll just call this 1.2 millimeter. PCIe bracket slot width, we'll call this 12 millimeters. All right, so what we'll do is we'll define this height here as parameters PCIe bracket thickness, and then we're going to define a spacing here of parameters slot divided by 2. Then we're going to bring the other one in, doing the same thing on the other side. Divided by 2. And that will give us, and so what we're going to do is we're going to do a pad. Might have to do a reverse pad on that just to make it happy. So we'll go back to our part design toolbox. Nope. Part design toolbox. We're going to do a padding. It freaked out because it needs to be reversed. 3 millimeter, just because I forgot to define a parameter for this. Let's go define a parameter for this. Enclosure thickness. This will define the exterior thickness of it. We're going to go 3 millimeters for now. I probably need to do more in reality for structural integrity, but we'll do this for now. And so this first pad needs to be changed to the parameters of enclosure thickness. Alright, and then the second pad needs to be that as well. Then we're going to need this first pad is enclosure base. Enclosure bottom. And then the next one is renamed motherboard enclosure. There's motherboard standoffs. And then this pad is the enclosure PCIe slots. PCIe bracket slots. Enclosure, actually we'll call it closure bottom slots. In that PCIe slots. Okay, cool. And then we'll do one more just to sate my curiosity here. We'll do one more reverse padding to just close that up. Sketch. We're going to import external geometry and also do that. We're going to do a full-on rectangle here. We're going to make these 2 points coincident. Define a height here of, we'll just do the slot. Parameters, PCIe, bracket, thickness again. Close, we'll do a padding, reverse the direction of that. We're going to do parameters, enclosure, thickness. Okie doke, that gives us a little slot hole there. This will just let us test our, this will just let us test the placement of, what do you call it, the stuff. And actually, because this is a test, what we can actually do, just to make sure the alignment is right, we could actually, rather than doing what I'm doing here, we're only going to do this for the sake of this test, but we shall do yet another sketch. Gosh darn. Sketch. I'm going to import external geometry. Nope, that didn't work. This circle. This is a hack. We're not keeping this. This is just for the sake of alignment, for the sake of this test fit. And so what we're going to do, because we know that these holes are supposed to be 3.96 mil or 0.16 inches, what we'll do is we're going to basically make a 3 point, actually, you know what? Since I've got one of these here, and I've got my calipers, how big is this darn hole? It is 3.8. All right, cool. So we'll set up a 3.4 mil. We're just typing these in because these aren't actually staying here. We don't need them to be perfect. 3.4 mil. And then what we're going to do is we're going to close that. We're going to pad this. And these will be parameter. We'll make these just 10 millimeters tall. And these are essentially, these are going to be our alignment pegs just for the purpose of the test. Just for the purpose of the test. We're going to delete these in just a second. We're just going to keep them for the purposes of printing. And you know what? I'll actually make them 3.6 because dimensional accuracy of circles is pretty good on most 3D printers. And all right, so we have our test article for the alignment of the PCIe expansion slots. That took a while, but we did go through this and find all of the numbers that we needed. So hopefully that's good. So what we're going to do is we're going to then save this NAS parts. We're going to export this as, put this on my desktop here, why not? Desktop, expansion port placement test, save. And I'm going to turn on my printer. All right, turn on the printer, make sure the build chamber is clear. All right, perfect. And then we're going to open up Bamboo Studio. Binaries, Bamboo Studio. I don't want to update yet. Prepare. Place NAS part expansion slot. Ooh, that's, you know, not the smallest thing. So yeah, we've got, let me go to my device, Nate's P1S. We got our PLA, CF. I did change the spool that was in here, so it'll figure out what I just did. I put an actual bamboo spool in this one, so let's see if it can figure out that it is a bamboo spool. It did, in fact. Okay, nice. Oh, wow. I gotta change the I gotta change the filament packs in my AMS. Or filament packs, sorry. Desiccant pouches. Alright. Yep, PLA basic color. Perfect. I gotta use this spool up. It's the one that came with the printer. Okay, so we're gonna use that. We're gonna go back to prepare. Color 1 is gonna be PLA basic. We only need one color for this, so yeah. Remove. PLA basic. Slice that. It's going to take us 31 minutes to print, so we got a ton of time that we can go start modeling things again. All right. Do we have all the parameters that we need? I don't know. I believe we do. Display all. Oh no, I don't want to display all travel seams. Yeah, we'll just take all of these standard parameters. We'll just, I think the only thing I want to do is I'll change that to 3 walls, slice plate, yeah, 31 minutes. And doing the standard, for doing the full print for this case, because it's going to be huge, I'm going to swap out for the 0.6 mil, maybe the 0.8 mil nozzle. But I just got my standard 0.4 mil in there right now. Oh, the kittens are waking up. Hi, Sagwa. How you doing? Yeah, babies. Yes, I've got my little kittens that I adopted, I guess last Tuesday. They're very cute. One of them hasn't quite figured me out yet. The other one wants to be in the same room as me 24/7. The one that is currently up and active, this one that's now biting my hand. Well, she's licking my hand, but she's thinking about biting me. So she's the one, the classic Siamese color. She's the one that wants to be around me 24/7. The cream color is still trying to figure me out. She likes being held, but during the middle of the day, she runs off. But either way. So yes, printer's up. We've got the sliced print plate. We're going to go to P1S, PEI. We're going to use Tron bed leveling because the thing's been off for weeks. Yeah, so send. Awesome. And these kittens are like, what is that sound? I've never heard that sound before, because they've been living in my office here, but they haven't heard the printer start up yet, so this is all brand new experience for them. Alrighty, so we'll just minimize that. It'll pop up occasionally to annoy us because whenever printer events happen. I mean, what am I doing? I can snap this to the side here. I'll have to manually resize windows. What am I doing? Alright, so first thing I do, we're going to delete these little, first thing I do, we save this. Just going to we're going to do the old classic, tried and true, not actually backup technique of Zip. Actions. Wow, it's already viewed as an archive, so it doesn't, like... God. Okay. Fine. Copy. The home. Paste that there. Why not? Okay. This is the most horrible way of saving things. Okay. Technically, I've got this. It's in my C file, so theoretically I should just be able to restore an old copy, but whatever. Okay. So we're gonna delete that pad because gross. All right. So now we actually have to turn this small test article into the full-on actual PCB. So I believe the enclosure bottom, yeah, we modeled it where this axis is the base of the PCB, right? So what we need to do is just gonna delete this. What is this constraint? I did this as one of those centered rectangle things, so I gotta figure out what this constraint type is. That is the little arrows that define constraint 40 mil constraint. I don't actually know how. There's a couple of these constraint types that I don't actually know yet. Constraint symmetric, create symmetry between 2 points with respect to a line or a third point. Okay. Well, so we're gonna have to. Oh, Jesus. Recompute. Oh, it's fine. Close your bottom sketch. So we got to adapt this into the actual motherboard. So remember that the y-axis here is the the y-axis is the base of the PCB. So what we actually would like to do is draw or stretch this side out to be the full area of the PCB. Oh, why did that? That's funky. So again, we're going to figure out how to delete these little constraints here. Do that. Now it should stretch, right? Oh yeah, now it'll float around. Okay. So now what are we going to do? Because I believe I've referenced it all to the top, I think. It's fine that this is the center, it's the center of the center line of the motherboard, but, oh god, no, stop. So we're going to delete this constraint. So we're going to assume that anything to the left is, sorry, so we do have to do a constraint of one of these sides too here. We'll just fix that as parameters PCB board height divided by 2. Just to parameterize that, we'll parameterize that one because we didn't. Board height, cool, parameterized, and then we need to. Careful, baby. The kitten's messing with my stuff. As they do, you know. They're very cute when they're doing it too. How can I ever be mad at her? How can I ever be mad at you? What did you even knock over? Oh, okay. Nothing important they knocked over. Nothing actually fragile, you know. So, all right. So we're going to define this as essentially the distance from the PCIe card, or however much spacing we need. I'm bad at this. So we got PCIe expansion. I actually just call this board edge to case, board edge to enclosure left. This is left from a, and this is, okay, sorry, the camera's inverted in my own perspective, right? So I'm going to try to flip this in my head for you guys. So if you have the two sides of the enclosure, you've got the I/O shield on the top. We're defining the left side as this side, so you're right. So if we got the sides of the enclosure, and then we've got the top of it, the left is this part. So I think I've got this perspective-wise correct for you. So the The enclosure, board edge to enclosure left, it will be this spot. So if this is one side, this is the left side, this is the I/O shield. We're talking about this parameter right here between the board edge here and the expansion area. Yeah. So we're going to define that as just 20 millimeters right now, which is a number I just pulled out of thin air. It is. We're going to definitely need to change that number. It's just a temporary parameter that involves this not changing size on me. So to define that, parameters, board, edge to enclosure left. And then we're going to say board, edge to enclosure right. We're going to also call that 20 millimeter, or we'll call that 5 millimeters for right now. This is actually going to be quite a bit. We'll probably have these numbers computed parametrically in the future, but this at least just gives us a way to include this into the into this sheet. So this will be, because we defined that as the board edge, parameters board edge to enclosure right plus parameters board width. That'll scale this out for us. We've got our one expansion slot, and this is actually going to end up being our case rear, our enclosure rear. So this will be where the I/O shield is. So now we're going to modify our standoff drawing to include the other standoffs. So we're going to go to the motherboard standoff sketch, and we're going to define 2 more circles. And the, oops, and the dimensions on these will be the same. Parameters, standoff diameter, and it'll be standoff diameter. And these are going to be horizontally constrained. And these are going to be horizontally constrained. Yeah. Actually, I take that back. No, they're not. These are not horizontally constrained. Because this is actually inset, sorry. So we're going to actually do, we're going to take a point here, just to make our math easier. These will be horizontally constrained. These will be vertically constrained. This is also vertically constrained. Yeah. And I do believe that these are horizontally constrained. So we do have a dimensionality on this. So that was F to J. Parameters, well actually we don't have an F to J parameter, but we do have a, oh, oopsie. I broke it, I didn't break it, I over-constrained. The vertical, sorry, the vertical constraint here is bad. Nope, that's, oh god. That's one complaint I have about FreeCAD is, when you over-constrain things, it really freaks the hell out. Alright, vertically constrained. This needs to be vertically constrained. Okay, now it is. And then the distance between here and here is well defined. That was our parameters C to F spacing, and then we have a C to F inset. Parameters C to F, CF inset. Alright, cool. And now that we have those, we can go in and define our holes, or yeah, the holes. Parameters, hole, standoff hole. All right. We can do parameters, standoff hole. All right, printer is printing. Again, if anybody watching has any questions or comments or wants to know anything, please just drop a comment. I do try to look at it every couple of minutes. Okay, so now we've got our motherboard standoffs. We've got the motherboard defined as basically everything to the right of the y-axis and then everything vertically. All right, so close. So yeah, so these are all our mounting holes for the motherboard. That's our hole for the PCIe slot. And this is this little piece right here will become the rear of the case. So actually we can just define that right now just to help us visually. No, sorry, it's this pad right here. We'll define this as parameters, enclosure thickness. All right, yeah. So that will be our rear of the board, or the rear of the case, anyway. Alrighty. We will have to add, essentially, margin onto the PCB just to make sure that we've got, at least onto the back side. Well, I mean, who knows, actually, on the back side what we're going to need. But... okay. Now we do it on the print. 19 minutes left on the print. Okay. Oh, what did I do that for? Sorry. Alright, so next step will be cutting out... well, we're going to define... actually... we should probably figure out where we need... actually, just to show you the automatic recompute thing, too. If we change this enclosure right, let's say we need 50 millimeters, right? This is now far wider, right? Right, so... and this is now smaller again, right? Alright, cool. So we need to figure out, actually, how wide we want the inside of this enclosure to be. So I'm using a GeekPi 8U server cabinet. I'm trying to find the actual DeskPi store, Rack-Mate. Cool, we should get the mechanical dimensions here. So the that's great. Those aren't helpful. Those aren't actually all that helpful. That shows us the width of that tray, not the actual width of the... oh, look, Jeff Gearling. Okay, I need... oh, jeez. Optional accessory. I need the full mechanical dimensions of this rack. Where are you? Alright, here we go. Maybe. No. Okay. I want the actual width between the two posts. It's probably 10 inches because it is a 10-inch rack. So I don't know if 10 inches on a rack means the holes are 10 millimeters wide, or if the or 10 millimeters, 10 inches spaced. 10 inches spaced, or if the actual opening in the front is 10 inches. So let me don't think my calipers are wide enough, guys. No, my calipers are definitely not wide enough. Okay, let me... I got a yardstick. Let's go grab that. Okay, got a yardstick. Here we go. How wide are the two bars? Oh. Exactly 8.75 inches. Okay. So. I think Kitten's really interested in the rack. Hey, don't eat that, please. 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 Please be a good kitten. Don't eat stuff. I mean, eat your food. Don't eat my things. Okay. Oh yeah, so 8.75 inches, which I believe was in fact defined on one of these. I thought that was the tray width, but it was the tray width, but the opening in the front is 8.75 inches, and the distance between the spacing holes, or the mounting holes, is also not 10 inches. What is 10 inches on here? I don't even know. Alright, that's fine. Because the holes... Those are like 9.93 out. Hey, stop. The holes are like, what is that? 9 3/8 inch spaced. Thereabouts. 9 and 3/8 inch spaced. Which probably is defined in here. Anywho. There's probably a okay, hold on, 10-inch rack hardware or 10-inch rack dimensions. Okay, so hole to hole is exactly as I meant. Yeah, 9 3/8. I was thinking by 9 3/8 by that moment. 9.312. It's not even square in any of these. So, okay. So yeah, but 8.75. That is what I measured. So, oi, kitten. No, don't eat the wires, please. Look at this. Look at this little gremlin. Look at how cute she is. How can I be mad at one of these? You know, they are adorable, but they like to play, and you know she wants down. Okay, go down. Be free. Don't eat my wires. Comes back to eat the wires. you little goober, come on. Oh, now she's a little sad. Oh, and she's chasing her sister. She's happy again. Okay, cool. All right. Right. Okay, so the enclosure width ought to be no greater than the opening in the front. They're going to say 8.75. I'll just say 8.7 just to give us a little bit of margin. So we're going to say enclosure thickness. I'm going to say one row above. The enclosure width has got to be equal to 8.7 inches. And just to make that a better number, we're going to say 220 millimeters. Equal to 220 millimeters. Because it's like just less than 221. So yeah, 220 millimeters, not mil, that's different. I gotta clarify that because I do intend to do some PCB design videos, streams, whatever at some point, and outside of the United States, if someone says a mil, they're probably referring to a millimeter. I almost assume they're referring to a millimeter. But if you're inside the U.S., somebody decided to rename. So there was a unit called a thou, which was, I believe, 1,000th of an inch. But somebody along the way decided to call it mil, M-I-L, mil, and that is 1,000th of an inch. So if you're in the U.S. and you're talking to people who are commonly used to designing things in imperial units, and you say a mil, they might think you're referring to 1,000th of an inch and not a millimeter. So I gotta be careful. And it's especially common in PCB design stuff, because a lot of boards are, the physical dimensions are almost all metric, which is a good thing. So, like, it'd be, 100 millimeter by 100 millimeter PCB, 150 millimeter by 75 millimeter PCB. But trace widths are commonly measured in thousandths of an inch. So you might say I want a 200 millimeter by 200 millimeter board with 8 mil traces. So you're defining the dimensions in, millimeters and metric, and then you're defining your trace with an imperial for some damn reason. So, yeah. So anywho, we're gonna measure the depth. So this Geek Pi rack, that's also one of the things. Rack depth is not part of the standard. I don't believe it is, because I've definitely seen some server racks that are longer than others. So let me go back to this Desk Pi thing here. So it says 200 millimeters. I don't know if that's piece to piece or if this is 200 millimeters. Let me get my trusty yardstick again. Measure these. Hopefully I got, there we go. I got the metric side. Okay. Yeah, 200 millimeters. 220 centimeters, 200 millimeters. That's about right. Yeah, 200 millimeters. Yep, that's the depth. Yep. All right. 200 millimeters. Enclosure depth. That's gonna be 200 millimeters. Perfect. What is Kitten doing? I heard one. Where are you, baby? Okay, interesting. Let me close the window. It's getting cold. Oh, there they are. I'll be right back. Close the other one. Okie dokie. Sorry, I'm back. Alright. So we need to define now. Okay, now what we really need to do is define how much space we need for our PCIe card. So there's definitely a standard for how tall these are. I know that for an absolute fact. There is a, okay, so PCIe card height. One slot clearance. I mean, okay, wait a sec. If the slots are 0.8 inches apart from each other, then the board, then the PCIe card cannot be taller than 0.8 inches. That's right. Right, because we have this specification that says that. Hold on, it's down here. Yeah, 20.32 millimeters or 0.8 inches. Let's spit on my screen. Great. Okay. So, right. So, therefore, the card cannot be taller than that, because how other? Yeah. So we need to define. basically more. Yeah, so we'll give ourselves 0.8 inches between the board edge because the center of the slot is inset from the edge of the board. So actually, sorry. So we'll define our so we'll define. Actually, it's fine. Okay, so enclosure left. So we're going to say that we need PCIe card slot center to the center of the next slot is 0.8 inches. So we'll just do a PCIe slot spacing. That is just 0.8 inches. And so... let's do that. So enclosure left. So what we're going to need to do is we're going to define this as how much past the edge of the board do we need the wall of the thing to be. And so that's going to be board. So that's going to, so it's going to be PCIe slot spacing minus. So this is, we're going to define this as board edge. So how far from the edge of the... how far from the edge of the board do we need to the wall of the enclosure? And so we need to subtract from that 0.8 inches the inset of the PCIe slot itself. So we'll do slot spacing minus board edge to PCIe slot center, which I mangled the name of. Oh, yeah, board edge to slot. Oh, 5 millimeters, perfect. That's a very... oh, no, sorry, right. It's this 12.4. Dirt. Okay. So NAS parts. So we're going to go into our sketch up here just to look at it. Yep, 12.4 millimeter, sorry. All right, so... and then... thickness. So then we're going to say, we're going to define up here, so we're going to say the enclosure, so we're going to call the enclosure tray the actual dimensions of the bottom inside of it. So we're going to say the enclosure tray width is equal to the enclosure width minus 2 times, interesting, minus the enclosure thickness, right? Enclosure thickness, which I got wrong again. Tick mark home equals. Nope, that's wrong. Oh, what did I do? Equals enclosure width minus enclosure thickness times 2. Perfect. Right. Actually, another thought here too is that technically, one thing we could do to try to save some, to give ourselves a little more margin on the size, is what we could do is define the area that the I/O panel sits in as the ears on the backside that actually bolt into the. Got a few. My older cat doesn't really like the kittens too much, but they love to follow her around. So my older cat is in here, and by older cat I mean she's like 12. She's an older cat. The funny thing has been that she's not doing very well, So I got the kittens to kind of soften the blow, but I have noticed that as the kittens have been, but she's never liked. For many years she hasn't really liked toys. But ever since the kitten started playing with some of her old toys, she pushes balls around and stuff again. It's kind of cute. But Still, either way, kind of sad. But either way, so back to this. So I'm thinking that one of the things we do is just to make better use of space. This what is currently the rear of the enclosure is actually going to be it's actually going to be open on the back face, and part of the ears that screw into the rear of the case will be the ears that screw into the case will be the actual back surface of it. So the tray thickness per se is sorry, blanking again. Very sorry. Yeah, while we have to worry about the physical volume of the width so it fits between the two vertical rails of the case, we actually we want the inside of the case to be flush with the rack vertically, or depth wise. So yeah, so we don't need to define a tray parameter for the back. So we just the tray width is all we're really worried about here. And so if we have a hard definition of the slot to center, then we can compute this from, we basically say is equal to parameters dot enclosure tray width minus the board width plus board edge to enclosure left. 31.6 millimeters. All right, cool. And so this whole thing should now be 214 millimeter. Perfect. That gives us our one slot here. With our the depth that we want. We're going to be able to have space to put the vertical walls in. Hey, you. How you doing? How you doing, baby? And one of the kittens is like right there. Hey, you. Hey, you. Hey, you. Yeah. Here she is. A little bit. She's a little less happy about being held. Yeah, I'm sorry. I'll put you down, huh? Or do you like this? I'll put you down. I'm sorry. This one, on the other hand, loves being picked up. She'll try to get down, but she'll sit here. When she's not trying to play with her sister, she'll sit here and want to be held. All right, so printer just finished, so we'll check that. Alrighty. Perfect. There we go. Alright, pop that off. Take off the little priming thing. Why is this not clipping back on? Hold up. Nope, I'm having trouble rewinding. There we go. Perfect. Alrighty. Hey. So let me turn the webcam back on. Let me bring over the desk cam so we can check alignment. Turn the light on. Because it is now dark outside and there's very little natural light. So we're going to do desk cam. Perfect. All right. Push that out of the way. Take our board here. Let me rotate it vertically here so I can see what I'm doing. And so theoretically, a couple of print errors. It's fine. just push that through just to clear that out. Right. What am I hearing? Sorry, I gotta check on what the pets are up to because I hear noises. Button, what's up? What's up, Button? Just have a bag. Hey, Button, Button. Alright, sorry, just had to check what the pets were up to. Okay. Yes, and now the kittens follow me back in now. They're probably expecting dinner real soon. Okay, so we've got slot test fit. That test fits good. Seemingly perfect. That's just a printer error. Alright, so hole test. Hey, look at that. They line up just right. The holes anyway with the standoffs. And then if we put the expansion card in here, it's looking not great. Hold on. I'm gonna push that in there. Stand this vertically, anywho. And then we'll put these in here. And, oh, this is slightly bent. Alright. Put these in here. Did I do that backwards? Hold on. Ooh. That's not looking good. It's not looking right. It's almost there. I don't know if that's just this expansion bracket or not. No, that's off by a decent amount, actually. That's unfortunate. I mean, it's not that far. It's maybe like a millimeter? Oh, they're almost lined up. Just not quite. I don't know, that's more of a printer error than anything else. I mean, is that... How much is that? A millimeter? A little bit? Maybe? Something? What fudge factor do we need here? From the edge of the... No. I'm going to make this aligned here. Two whole millimeters? That's a huge fudging. Hold on. It might be a good whole 2 millimeters. Ugh. Even more. Hold on. 2.5 millimeters? How did I don't think I messed it up that much. I think these numbers I've been following are not necessarily the greatest. Either that or my... Oh, you know what? I might have this turned around. Oh, I can't have it turned around backwards. It's impossible. It's not like I can flip it any other way. No, I got it in the right spot. How's it 2.5 millimeters off? That's eyeballing the center. It's probably more like 2 millimeters. Yeah, 2 millimeters maybe? Okie doke. So what we're gonna do, we're gonna adjust this number by 2 millimeters. Did I flip it? Did I flip the inset. Oh, wait a second. I might have. So I flipped that. Hold on. I might have flipped the dimensionality to the center of the slot. It might be. I did it in. I did I used that number and I went inwards towards the center. I might have supposed to gone outwards, and since it was 0.75 mil, it'd be about 1.5 millimeters. That's pretty close to what this is off by, I think. No, it was. Oh, wait a second. Inset? Hold on. What did I... Something's funky. Hold on. Sorry. What did I do in here? No, what do I got going on here? Save, cancel, close. Alright, sketch. I set this as 0.75 mil off the edge of the board. Ooh, the print came out with this being closer that way. Basically the center being off the edge. Which, I mean, it's not. I did it backwards. Okay, I did this backwards. That's my bad. So this is, in fact, the... This is in fact this, but I messed up. It's supposed to be the other way. This is supposed to be on this side. Okay. I'm pretty sure. I mean, that's what it looks like in here, right? It looks like the center line is further inset on the motherboard. Let's dial this to 0.75 millimeter. 0.8, that's close enough anyway. Close enough, maybe. Well, we shall make this adjustment and retry with that other file, because I think that's what I did, but might as well spend a very small amount of plastic verifying our whether we fucked up or not. Alright, so let me back to the desktop. Turn off this light so it doesn't annoy me. And flip this back around. Okie doke. So we change. Right, you were looking at the desk cam the whole time. Okay, sorry. What I did, I fixed it in here. Let me go into the other one. NAS parts. No. Open with other FreeCAD. Oh, come off it. Okay. File, open, home, FreeCAD, NAS parts 1. Perfect. This is our old file. And what I fucked up, or what I messed up, was this part. I was supposed to put this on the right-hand side, not the left-hand side. That's supposed to go here. Simple mistake makes big changes. Okay. So, at least I'm pretty sure that's what's supposed to happen, Yeah, 7.92. board edge to PCIe card top side minus, you know, that card bit plus half that. Yeah, yep. That's what it was supposed to be. And I'm okay. Yeah, I got it flipped in my mind. Okay, cool. So we're gonna re-export this. Export. Save it again. Overwrite. Go back to our printer tool. Prepare. Just so we're really confident. Let's look at the slot. We're gonna reload from disk. We see that moved a bit over. All right, cool. And actually, just to make this a bit easier to see, we defined this. Oh wait, no, we defined this pad here. We're just gonna make that 3 millimeters. Cool. Just to give us a little easier time, preserve the hole a little more. All right, so we'll export that again. Save that, overwrite, reload from disk. Yep. Oh, wait a second. Oh, it recentered. That's right. Okay, cool. So yeah, well, this is now our test article. We're gonna slice the plate. We're gonna run the printer. All right. Print plate. Send. All right, and we got our nice little piece of trash here. 18 grams of trash. At least the hole placement was correct. We did learn that. So yeah, so close. Let's just make sure that we, yeah, so we moved the little dot there. Perfect. Close. Yeah, all right. So yeah. Just to make sure we're good, we're gonna do enclosure tray depth, or enclosure depth, enclosure tray depth. That is going to be enclosure depth minus PCIe bracket thickness. That just this parameter just lets us make sure that we're accounting for that little bit on the end that holds our PCIe brackets, our our expansion card brackets. So we'll do that. Or sorry, we're gonna do that. Name that the alias. Perfect. All right. So we now need to define let me make sure that none of these standoffs are referenced to the bottom of the board, which they're not, which is good. Because what, again, we need to do is enclosure bottom. What this will actually be called is we need to rename this the enclosure tray rather than bottom. Do we call it the tray? Yeah, we'll call it the enclosure tray. Close. And so what we do is make sure this whole vertical bit here is the height of, well, we're going to keep the center just because it's parameters board height divided by 2. This is going to be the parameters.tray depth. Hopefully that didn't mess anything up. Nope, no it didn't. Good. Cool. Alright. Alrighty. We've got our slot. We've got our motherboard mounting. We've got our motherboard justified to the left. And we've got, let's see here. Now what? So we need to start building the vertical bit. We'll start building the walls of the enclosure. So we do have the tray width. So we're actually going to delete this back section here. So... Need to model. So yeah, actually, let's leave this just for a second. What we're going to do now is we're going to set up another part that is the ears that'll mount on the back. Actually, we could integrate the ears into the case. We could do that. Okay, yeah, you know what? We will actually integrate the ears into the back of the case. So we shall. This is the that's just the back bit there. This is the full tray width. We're gonna need to define the walls. Actually, no, another thing we'll do, actually, we're just gonna do this right now just so we can see. We're going to define a, what do you call it? We're just gonna make a simple little square just so we can see the volume of the parts. So this is actually going to be enclosure. And then I'll rename this to enclosure body. Okay, and then we're going to place this, we're going to call this motherboard. Motherboard mock. Create a body. Name motherboard mock. Sorry, rename it motherboard mock body. Sketch. Y plane. Hide this. Rectangle. We'll do that. This just define it with the same parameters as our other thing. This is going to be parameters, board height, divided by 2. This whole thing's going to be board height. Define this as board width. Alright, cool. Then we're going to close that. We're going to define a pad. The pad's going to be parameters, thickness. It's a PCB. It's probably got the same thickness. I'm going to turn on the enclosure again. What we'll do is we'll then translate this up by cancel space. The placement on this part is going to be position. The z-axis is going to be standoff height plus enclosure thickness. That should sit the board right there. Yeah. And so this will mock the motherboard. And we will then define another mock that is a standard sized PCIe card. Or at least the length of this one, because this is the one we're using, right? So turn this on. Hope the thing's long enough. Find out that it's not. Yeah, alright. Well, I'm going to go to the internet, or at least find the meter stick again, the yardstick again. Oops, don't poke my monitors. Yes, use a centimeter side, like civilized people. And we're looking at 16, we're looking at 165 centimeters. Millimeters. There's, but actually no, it's beyond the half of 160 7.5. It's basically 16.75 centimeters. So we'll just call it a even 17. But again, I don't want to deal with this. Okay, so we can. I just want to mock the PCIe card at some point, but we'll try to do that. We'll try to mock it at least. We won't necessarily get the we'll get the XY constraint correct. We won't get we will get the Y constraint and the positional constraint, but we won't necessarily get its exact placement in the Y correct. So we'll do another part. I'm gonna rename this part to network Nick mock. Create a body, rename Nick mock body. I'm gonna do a sketch. It's gonna be on the YZ plane. I don't know, we're gonna define I'll do a good old centered rectangle on a Z-axis. I'm gonna do a full height PCIe card. Full height PCIe card height. PCB. All right, here we go. Nice. That's yeah, okay, fine. 13 years ago. So 100 man, that's a rougher one to read. Okay. All right. Oh, it's 106 minus 7.24. So we got like 199 like 100, like 10 centimeters tall, maybe, right? Maybe. Yeah. So we'll just find this as 10 or as 100 millimeters. And then how is this carded? Who knows, man? Okay. 174, right? 175. Why not? Why not? We'll just do that. Close. I'm gonna pad that out to, again, card thickness. PCB card thickness. Okay. Then we're gonna look at it from the front. Which I guess it's the back. My dumbness. So that's gonna be, oh well. It's the center of the card minus half the thick. Oh Jesus. Okay. So position is going to be, so in the x-axis, it's going to be parameters, PCI board edge, PCIe slot center minus parameters dot thickness, card thickness divided by 2. Okay, we're seeing a bottom number to, so 34 millimeter between the board. So position nickmock Y. I don't even know what that how's it even referenced to. Okay, anyway, transform. We'll just do. We don't actually need this to be accurate. It's just. In general, it's like half the standoff, but it's fine. This is just for our own reference sake. All right. All right. So, realistic all all we're really concerned about is the enclosure, right? Show. All right, so we've got this object here, and so now let's start building the sides of the enclosure. So we're going to define sketch. Do a sketch. Nope, I don't want a copy. I want this to be the active body. We're going to do a sketch. We're going to import external geometry, the sides. And then we're going to import the external geometry here as well. We're going to create 2 rectangles. So these will be the enclosure thickness, parameters, enclosure thickness, parameters, enclosure thickness. We're going to do a coincident point here. Make these 2 points coincident. Oop, that didn't work. Coincident. Cool. I'm going to do coincident points. Coincident points, perfect. And then we're going to do the enclosure, insert 1 row above, enclosure height. And that'll be, I'm going to do this whole enclosure, we're just going to say 2U for now, so that's 1.75 inch, well actually I should do that in here. That's 2 times 1.75 inches. We're actually going to be targeting a 4U enclosure, but with the hard drives installed, so anyway, back to here, do that. We're going to, oh, I should have attached this, oh, I did this wrong. The sketch attachment should be actually flat face. I need to select this plane. Okay, I messed up. Okay, sketch. Oh, it's really mad at me. You know what? I'll just delete the sketch. Or redo that. Sketch on the bottom. Then we'll do rectangle here. Rectangle here. We're going to do GX for import external geometry. Import that. Import that, import that. Cool. And make these coincident. Again, we're making the walls. We're going to do coincident points here. Coincident points here. These are the thickness, so parameters, enclosure thickness, copy that, do this again, enclosure thickness. All right, cool. Close. Then we can do a pad, reversed pad of parameters, enclosure height. And see how our PCIe card like extends up beyond the top. That's why. Actually, you know what? We're going to define this as 3U, just so we can see. Yeah, there we go. So you basically need a. You kind of have to have a 3U enclosure to include a full height PCIe card, but that's fine. And again, we're going to eventually edit our rack ears here, or we're going to call these our ears. Actually, I should probably just have deleted this back piece before I padded the sides. So yeah, actually, let's delete that. Cancel. Delete this pad here. Are you sure you want to continue? Yes. Delete the sketch. We're going to re-reference. No. We're going to re-reference this sketch to the bottom face. So flat attachment support. is going to be Enclosure PCIe bottoms. Okay. Do a flat face mapping mode. Do that. Okay. Still bad. Engine 3D. I got face 4 sketch 2. Map mode. We actually want the map mode to be just a face. Okay, yeah, there we go. Oh. Oops. Oh. Okay. Dang it. Alright, we're going to create the sketch again, because I'm doing this. Okay. One last time. Bottom. Select. Sketch. Alright. Import. External geometry. External geometry. Import. Alright. Rectangle. Dupe. 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 Width. Define as. Wall thickness. Define as. Wall thickness. Coincident points. These. Coincident points. These. Coincident points. These. Points. These. Alright. Cool. Close. This. Pad. Reverse pad. Parameters. Enclosure height. Alright. Good. There we go. Now we're golden again. Perfection. Okay. So now that we got this, Alright. So what we're gonna do, we're gonna make the rear I/O panel, and no, it's gonna be 0.8 inches. So let's. -1. Yeah, we'll have enough room. Just enough room. 7 inches. Yeah. All right. All right. Do. Because yeah, kind of the thought here is that with the fact that the back is going to be, what do you call it? Sorry, I'm blanking here. Sorry. With the fact that the, oh jeez. Sorry. The fact that the hard drives are going to be in the back here. So hard drives are 3.5 inch, or 3.5 inch hard drives are 3.5 inches wide. Who'd have guessed? So to them side by side, closest they could possibly be, is, you know, no spacing, so that'd be 7 inches. You obviously want some spacing, so I kind of want to try to, I would kind of want to give them an inch, like, because I need the mounting hardware, because I want to put 2 drives left and right, and then 2 drives left and right and 3 vertically, which is fine, but I need to clear this PCIe card. So if it's 8.75 on the back, and like, let's say this 0.8, if it's 8.75, this 0.8, so that leaves us with 8 inches. So we got 7, but this just barely works. Basically gives us 0.3 between each drive. We'll have to be a little creative. Because maybe what we do, maybe we actually do turn them vertical. Maybe we turn all 6 drives vertical. Because they're how many is 6 drives? 5-inch drive height are 1.028. No, so let's say 1.25 times 6. Yeah, it'd be 7.5. It's the same. So it's a quarter of an inch between each drive. We could actually vertically mount, but then be 3.5 inches. So that would be 2U, 3.5. So 1.75 times 2 is 3.5. Yeah, they're literally exactly 2U tall. So and we need actually. I mean, we talked about doing a 4U enclosure. I mean that was the plan. It was a 4U enclosure. So the motherboard plus the heatsink is not completely. It's not. What do you call it? Blanking. I'm sorry. The motherboard plus its heatsink is less than 2U. So if it's going to take 2U for the drives, we've got a little bit of margin. So we might be able to swing this. I actually might be doable to put the drives all mounted vertically up to this point. We can try that. Just kind of ugly. Well, we'll figure it out. So... Alright, well, we obviously control. What else do we got going on here? I'm gonna try to mount the JetKVM. Okay. Yeah. We'll got a little bit of volume here. We might be able to put the JetKVM somewhere inside here. We'll figure it out as we further flush this out. So now let's. Printer looks like the printer's not almost done. It's got 6 minutes left. Okay. So hi babies, how you doing? Hi kittens. How you doing? Huh? You're hungry? No. I think they're begging for their dinner. So, here let's start modeling the back bracket here, and we'll. So what we're going to do, again, is we'll define this as the back, rear, rear I/O shield, and we'll do a sketch on that. And cool, it kept my centering geometry like I wanted it to. So let's define a. So we're gonna import. External geometry. So one of the things we might do is if we do this as a full hollow shell and we mount the hard drive cage inside of it. Yeah, we'll figure out structural integrity in a bit. Probably not quite today, but we'll pull external geometry. So we're in our sketch. Pull external geometry. Let me pull external geometry. Come on. It's G, X. Import that. Import. It's the bottom. It's fine. Import that. So we're going to say we're going to draw a rectangle. You don't have to define sizes or anything. Make those coincident points. Make these coincident points. Make these coincident points. And cool. And it'll auto size for what we need. And then so we're actually we don't want to do that. Actually, I take that back. Because we actually want beyond that. We want these to be coincident with the axis, but not the height, and these should be horizontally aligned. But we don't want the... Yeah, there we go. And so what we're going to do is we're going to say the ear thickness. We're going to define enclosure... ear width is going to be a size. And we're going to say enclosure ear thickness is also a size. And we're going to call that 5 millimeters for now. And the ear width, because we looked at the 10-inch rack geometry. So that's 10 inches is basically the full-on width. So the ear width is going to be equal to 10 inches. 254 millimeters, which is the exact maximum, almost just 2 millimeters shy of the exact print volume of my printer, which is why 10-inch racks are so popular in the 3D printing community, is that a lot of people got bamboos, and those are a 256 millimeter cube. Now, obviously, other people have other types of printers, fair, but 256 millimeters cubic is what a lot of people can do. So, yes, got this, yarp, and so we're going to define this as the parameters ear width. Alright, and I don't know how to do the symmetry, to be honest. Figure that out. How do I make... Well, anywho. We'll say parameters, enclosure width divided by 2. Or enclosure width, sorry. Ear width minus enclosure width divided by 2. There we go. That'll give us, that'll do it. Alright. And we're gonna do a pad. And that will be parameters ear thickness. Alright, perfect. Alright, we're defining the rear IO shield area of the enclosure here. Our Shorty McShort 3U server. I'm going to put some nice bolts in here eventually to hold the back ears on. Hi, babies. What are you doing? Alright, once the print's done and I check it, then I'm going to feed the cats, and then we'll get back to this. And okay, so we got that, we got that, we got that. Alright, yeah, now we've got... Yes, they're being very hungry and very naughty. Okay, so... What's the hole spacing like? We've got... They're inset by 0.25 inch. And they're spaced by... 0.625 inches. Okay. There we go. There's the printer. 0.25, 0.25. They're all sitting in my cable box because of just being too dang cute. Alright, so, the next thing we're doing are IO shield cutouts. That is what I believe the next logical thing to do is. So, okay, the print's done. Let me go check the print. Alrighty. I do love how modern printers are so fast that, I can actually doodle something up on stream, send it off to the printer, and y'all can see the result. So yeah, so let's go back to the the desk cam here, test fit this. So we're going to turn on the... So that's the bad one. Throw that out. Turn the light on. Hit the wrong button. Yes, I did. All right. Turn on the desk cam. All right, let me get it all aligned so people aren't actually here yet. Alrighty. Bring this up. New test article. Here we go. Oh, would you look at that? Oh, it's beautiful. There we go. Perfect. Perfect fit. Oh, yes. There we go. It's perfect. Alrighty. So, well, just about. There's a little more finagling that could be done, but just about perfect. So maybe I only need to adjust it by. Oh, it's so close. That's honestly printer. It's, you know, I'll give this guy online margin for that. I mean, it's almost perfect. I mean, we're talking maybe. That's 1 millimeter given my margins, so I think I gave it so it's like a 0.5 millimeter off. Like their numbers online are like a 0.5 millimeter. It's so close. Okay, like it's so close that it probably wouldn't have even mattered. So like that's so close. Yeah. So this is the test fit, right? Yeah, there we go. And I bent it a little bit. So printed this out of PTG, so it'll be a little more rigid. But yeah, so here we go. We've got we've got the two holes lined up, with the motherboard standoffs, and we've got the PCIe slot insert on the back. So we've got our expansion connectors. We now know exactly where they're supposed to be. So yeah, so we'll know that our layout will work. So yeah, I'm stoked. Cool. That I've been fretting about that specifically for like weeks. That's been one of those things that's been stopping me from getting started with this project. Was like, oh, can I even find the sheet of numbers that I need? All right. So let me bring this back to the desktop here. Turn off the desk cam. Lock my phone again. Turn off the camera. All right. So I will be right back. I need to feed the cats. So please, if you're interested, please just hang around for a little bit. Taking about a little bit of a 5-minute break here to feed the cats. Take a bio break for a second. I'll turn off the camera here. We're going to get right back to cutting out the IO shield here. People left when I said I'm going to feed the cats. Okay. Oh, well. All right. I'll be back in just a second. Okie doke, we're back. The cats are fed. Huh? Ooh, this is some nice PLA. But okie doke. So we're going to be cutting out the rear I/O shield now. So let's take a sketch. It's going to be centered where it needs to be. The board edge right here. So back to our design guide. We're going to say we've got doop-a-doop-a-doop. We've got, so the aperture is the first step. Mr. Ford, the I/O cutout or aperture is defined as 158. And the next thing is to draw the keep out area, front and back. Okay, so we need to describe the cutout specifically. So, all right, so we've got I/O shield. Shield width is 158.75 millimeters. 5 millimeters. I/O shield width. I/O shield height is 44.45 millimeters. Height. Shield height. And then we need to define, we're going to call it the board edge to cutout area. So that's this 2.44 millimeter number. So we're going to say board edge to I/O shield. And that's going to be 2.44 millimeter. How much NVMe will this NAS take? This NAS will take a total of I'm gonna 2 NVMe drives in it, and I'm gonna have 6 spinny boys in here. Because I'm trying to move over my existing NAS, which is 3 NVMe, although one of those is a boot drive. And then 2 cache slash metadata slash special small blocks disks, plus 6 high capacity spinners. So the right, so we've got okay. So the I/O shield here is referenced to the bottom of the PCB, which I need to be careful of. That's fine. We'll have to deal with the thickness plus the standoff height. That's good. So yeah, 2.44 is board edge to the cutout. Cutout's referenced here. Okay, cool. So we have enough to figure out the cutouts. Okay, so remember that we've got our board is, so the bottom of the case is on our XY plane. And then the vertical Z axis is aligned with the edge of the PCB. So what we can do here is we'll put a rectangle. We'll define our width as the I/O shield width. We're going to define our height as the I/O shield height. We're going to reference this to the XY plane, and remember this is going to be the thickness of the enclosure plus the standoff height. All right. And then we need to define a distance between the board. We need to pull in our board to board edge to I/O shield number here. Oh, wait. I almost fucked up. Okay, sorry. Very almost fucked up. It's over here. So, sorry. So we're going to define a point here. Because we need it to be, remember, this is our our card edge here, so the IO shield needs to be over here. So we go back to our sketch. What we're going to do is we're going to define a point. Actually, you know what we can actually do here? There's not a good reference. Okay, we're going to put a point on the x-axis here, and we're going to put a distance here of the board width. Parameters, board width, and then this is going to be referenced here. This is the parameters board edge to IO shield. Perfect. Okay, awesome. So we've got our IO shield cut out there. That's going to be referenced to the base of the PCB, which it is. Alrighty. And all right. Should maybe let's hold current. Right. I'll lick it. Okay. So yeah. So that's our rear IO. And now we need to do our PCIe slot cutout. So that will be, so we need to come back to here and reference the whole again. Remember we did this before, right? So, okay, what was this pat? No, cancel. Which was this one? This is the, oh. So enclosure sides. This is the enclosure rear. This is the, yeah. We're gonna do the PCIe slots, and if we remember here, we're just using that board edge to PCIe bracket center, and that's inward. That's inward, not outward. So yeah. Back to sketch 8. So we can do, yeah, we'll put a point here just so we can reference. That is PCIe to slot board edge to bracket center. Yeah. Okay. And so typically the, okay, and so let's see where this is referenced to. So we're trying to figure, we're trying to reference the base of the cutout. And so what it looks like is that the card height is 111 point. Okay, so yeah. I'm gonna do more math. Okay. So the top of the hole is 3.4 plus 111.15 minus 16.4. We get the top. So because we only have to use that once, we're just gonna wing it. I'm gonna put another rectangle here. Actually, we're going to put a centered rectangle because we actually do have the centering point. So we're going to define the bracket, thickness bracket, slot width. That doesn't make any. We're just going to call this motherfucker 15 millimeters. And the height. Okay, sorry. In the top, or actually, sorry, this centering and that centering, those are vertically aligned. This vertical axis is going to be 89.9. We'll just call it 90, because why not? And then it's there. We're just trying to control the position. So the board bottom to there is going to be formula, the quantity, 3.4 millimeters plus 111.15 millimeters minus, actually, ooh, and remember, this is reference to the base of the PCB. This is reference to the top of the PCB. So minus 115. Minus 16.4 millimeters plus the PCB thickness. So parameters, PCB thickness, PCIe card thickness. All right, there we go. So 99.9. All right. Theoretically, that slot's in the right spot now. Realistically, I don't even know if it matters. That looks in the pretty close there, yeah? So what we're going to do, now just so we can actually visualize what's going on, we're going to define, these are holes, or this is a pocket, and the parameter, the hole needs to be cut to the thickness of the ears, so 5 millimeters. So yeah, now we've got the holes that these cards are, and the NICMOC, we can move this placement, translate that, so we can see it. Yeah. So now we've got, you know, this hole is, well, I did this perfectly. Oh, well, right. We made it bigger than we were supposed to. So if we actually changed it to only be recompute object. Okay. Okay. Sorry. If we actually change this to only be 12.06 millimeters, right? We can actually see that it's very, you know, it's supposed to be 0.35 millimeters from the top, and we can see that it pretty much is. But we want to give ourselves a little more margin, right? There's no problem really with giving ourselves more margin, so we're just going to call it an even 15. B-Link's response to my Friday. Oh my! I'm so sorry, Danish. Oh, is this one of those like BER6, BER or SER NAS unit things? This is the one you just got, right? Alright. Alright, hey. So hopefully we don't do too much damage here with this. Very small. Yeah, it's like 2 months old. Yeah. How thick is this? And, all right, we're gonna try to measure the. Put zero out the zero out the calipers. Yeah, you know, the reason I wanted it to be 12 or 15 is because it is 18.5 millimeters wide, this support bracket. I mean, the actual, like, stuff in the middle of it is, I mean, not quite centered, but, you know, it is 10.5 mil. So if we do 15, and we got, it's, you know, pretty close to the full thing. Yeah, we definitely want 15. That is definitely more reasonable. Yeah, so we've got, hello kitty, hello kitten, how you doing? Yeah, starting to get a little tired now that you ate, huh? Yeah. Yeah. Also kind of annoyed at me for streaming and not paying attention to you, right? Yeah. Okay. All right, so we got those. Now we need to cut out the. We'll need to cut out a. We'll do something for the top of the, the L part of the bracket, right? Before we get into that though, let's at least just put in our mounting holes, right? Yeah. So we're going to go back to the sketch. We're gonna, and then the kitten's gonna push over the yardstick. It's gonna, and then yeah, we're gonna put at least we're gonna do the lower 6 on each side. Doot 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 doot. And these are supposed to be what is the diameter of these holes? Probably even dependent on rack. I mean, rack ears, rack mounting is always such a pain in the ass. But because you never quite know what it's supposed to be. Every rack supports installation of cooling fans. Standard number 10 by 32 threaded holes are present internally and externally. 12 by 32. That threaded holes are. So these are 10 by 32. That's what it's saying, right? I'm not insane, right? Alright, so number 10 by 32 screw. Is that an M10 or is this an Imperial, or it's probably an Imperial screw. Of course it is. 1032 thread size. Yeah, it's a 3/16 of it. The diameter exactly 3/16 of an inch. So we're gonna cut the hole at 5 millimeter. I mean, I guess. This thing came with a hardware kit. I always measure things. Try to put the box out with my finger. Here we go. Yeah, the kittens are super interested now, right? Hey you. Or at least this one is not. She just wants to be pet and play with my finger. And then the other kitten, though, the one that's a little more... She's the one that's still trying to figure me out is... Oh, hey, that's interesting. In the hardware kit is a couple of Raspberry Pi breakout boards. That's interesting. Okay. They're these, like, HDMI bracket things, but did it actually include any hardware for mounting things? Oh my... Yeah, came with a lot of hardware for mounting Raspberry Pis. Didn't really come with a lot of hardware for mounting things on the rack. That's funny. Okay. Well, I'm... Okay. Came with the tiny little ones, and then none of the big ones. Alright, so 1032... Oh, I don't want to squish a kitten. There we go. So... Yeah, so number 1032 screw, what, hole size, there's a 10, so that's say 3/16 of an inch, so that's going to be, screw size, number 10, 1032, minor diameter, we want the tap drill clearance drill is going to be a, free fit. I'm gonna do point. Let's take the middle, 0.20 or 0.2 inch. So, oh, that looks funny. See, you're gonna do enclosure ear diameter, closure ear hole diameter. That's going to be equal to 0.2 inches. Basically a 5 millimeter hole. Looks funny. Turn to switch cheese. Diameter, parameters, ear, hole diameter. Probably a way of bulk setting this. I just don't know what it is, so we're gonna do it this. I'm gonna do it it's annoying, but it definitely is gonna take me less time to just specify all of these like this than it is to learn how to bulk edit. Although in the long run, I really should learn how to bulk edit these constraints. That'd be a good thing to do. Okay. I don't have anything to do in the morning. I mean, this is just work. Alright, so these all need to be vertical. Can I do, yeah, vertical, 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 horizontal, vertical, 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 vertical. All right, and then these can be horizontal, 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 and horizontal. All right, and so now we've got, what was the spacing again here? So the bottom of the enclosure is the bottom of our thing. So we've got, 0.25 inch from the base. Be 0.25 inches. And then we've got, in between, inside of one block is 0.65 inches. .25 inches. Why is this broken? It's mad at me. I'm going to do distance to here is going to be 0.625 inches. And then it's going to be 0.5 inches to the next one. 5 inches. That's going to be back to 0.625 inches. And then it's going to be back to 0.625 inches. Perfect. Alright. And now we need oh yeah, and so now we need to do the placement. So if we know the width is exactly what we want from the rack ears, then we need to make these it's the inset, right? Inset is, oh Jesus, please tell me what they are. Is it really gonna make me do math? I guess they're centered, so it's 0.625 inches divided by 2. 0.625 inches divided by 2. Okay. 0.625 inches divided by 2. All right. I should have parameterized those, but you know what? Whatever. Okay. So we got those. And those are still part of our padding, or part of our pocket, so we're good on those. All right. So we've got our, now let's try to cut out something to mount our PCI Express connector onto, right? And you know what? I'm gonna, we'll do fillets and bevels and stuff at the very end. So yeah, starting to look really good. Starting to look pretty spiffy. Alright, and the rear thing's going to be held on by, we're going to put some, going to build some threaded bits into this back plate, and that's how the, sorry, we're going to put some threaded bits in the back plate here, and then have a back plate, put some threaded inserts, some big ones, like some M4s or some M5s, into like the four corners that'll happen, and then we'll, however many we need to screw the back plate on. Probably going to need some mechanism integrated into it to hold the power supply. Still need to figure out where to put the JetKVM. Although, due to the amount of space above the I/O area and below the cooling fan and between the side of the case, it might just fit into here in this corner. And then we might just put a capstone jack into here to bring the Ethernet out. But we're still thinking about how that's going to work. So I'm curious as to if I could just, I wonder how much PLA I've already used, or how much, how large this will be, because after I get, you know, to be honest, I mean, PLA is dirt cheap, right? So, and I don't mind wasting it. But just need to know that I got enough on the reel. Okay. Yeah. So yeah, let's see. What's next? What's next? I think that. What is next? So. I think we got. Right. We're gonna do the little mounting block so that the little L piece of the PCI the expansion connector can screw into here. That's what we're doing next. Right. So let's go back to our guide here and look at, what are the cats doing? Hey baby, how you doing? She's trying. There we go. She got up there. Where's the other kitten? Sagwa, where are you? Hold on. Where'd you leave your sister, huh? Where'd you leave your sister, huh? Where'd you leave your sister? There you are. Alright. So... Okay, yeah, so come back in here, figure out what this rear L thingy looks like. Okay. Kitten games. Saw. Oh yeah, I guess it does go to the right. Okay. I guess the hole is centered over... No, it's not really. I'm trying to figure out where the centering of the hole is for the mounting bracket. So... For a full height... it is. All right. 45. They define it, but how in? It's 2.54. Okay. Are you going to be nice to each other? You're going to be nice to each other? Huh? Hey, Shikwa. Shikwa. Yeah? How you doing? How you doing, huh? How you doing, baby? Yeah. I'm not doing as good. I'm annoyed at your sister. I see. I see. Yeah. Yeah. Okie doke. Yeah, we got the as far as the kittens go, they've got one very brave, very outgoing one, and then you've got one very timid one. But the funny thing is the timid one's the vocal one. So she's the one who makes a lot of noises. And today she did the cutest thing. You know, she was running away from her sister because her sister was annoying the crap out of her. And then she literally just jumped off of the cat tree into my arms. It was the most adorable thing ever because she's in the middle of the day. She kind of runs away from me a lot when we're like out and about, and I don't know if that's just because she's afraid of her sister or if she's afraid of my cat Button, my older cat Button. But either way, it was very, very adorable. And what are you doing? How are you doing, huh? You doing all right? Yeah. Yeah. Do you want to be picked up? I got you. I got you. I think that was the wrong thing to do. I don't think she wanted that. Oh, are you okay? Nope, you didn't want that. Okay, I'll put you back. Here you go. All right. Okay. So let's see. Right. L thingy. So from the top, we did define exactly the top of the slot cutout that we were thinking here. Or that it asked for anyway. So, and we did subtract that 10.16. So, we need to define the cutout as what do we do here? We need to define. Problem is, I'm kind of hesitant to put any kind of overhangs into here because kind of thinking of printing this using the angled printing technique. So I'm thinking of kind of printing this as if, you know, I build a support under it so that I can print it at an angle. Because if I print it face down, it doesn't have a lot of lateral strength because all of the lateral strength is on the layer lines. But if I print it at an angle, it'll be stronger. But it also involves not having any overhangs. I would also need to, I mean, it is 200 millimeters long, so I can't cock it over too much before the length starts to be an issue. 200 millimeter, what can I, because I can't print it at a 45, because we're talking about, you know, root 2 over 2 time, or square root 2 times the length. So, you know, 1.41 times the length. So if we're already at, I mean, you know, 200 millimeters times, you know, 1.4 is, you know, 280, right? So that's much larger than my build volume. So I can't actually print it fully. I think I can probably, can I get away with a 50-degree overhang on a bamboo? Well, I guess we'll see. We'll do a test print at some point. Oh, you guys swap places. Interesting. Okay, do you want the little toy to go back in there? There you go. There you go. There you go. Annoy the kittens. Okay. Right. So 16 in. Yeah, so we're gonna be 10.16 up. And then 1.6 up. And then it defines, okay, so that 10.16 to the base here, and then it defines more, or is that all the way up? 12.75. Oh, hold on. Hold on. So if that 120 isn't all the way down to this, and then they're constraining it. They're cutting out the width. Is that, you know what? Yeah, based on the, I mean, this is, I don't know if the relative sizes are correct, but it does look like they're probably defining this as the maximum, as otherwise there's no reference points to be had. So I think, yeah, I think this is, the top is 10.16 up from the top of the cutout, but then it shifted over. So we'll do, hell, whatever. We'll go back to the sketch. We're gonna do a little rectangle. Doesn't need to be centered. So we're going to define the base to the top here as 10.16 millimeters. We're going to define a translation over of 2.54 millimeters. We're going to define a width here of it's probably the same as the whole thing, right? They're just going to translate it over, right? So the width of the whole thing is going to be 17.5 plus 1.27, so it's going to be 18.42. Yeah. Actually, what the hell? I don't want to do that. I can also define this as a translation of 2.45. Still need a height. So what is the insertion depth into a chem connector? Well, actually, that's just that's easy. We just measure the height of a PCIe slot, the connector, right? Plus some margin. Gonna be like 8.5 millimeters or 11.25. Yeah, I mean 11.25 is just an easy number. That's easy to deal with. So we defined this as, I mean, that makes this still 15 millimeters wide, which is fine. Well, not fine actually, because we do need to fit this whole dang top connector through it. So that's going to be, and that's effectively, yeah, it's 19 point. 19 mil on this thing. So, I mean, there's a definition for it here. Realistically, what we need to do is, you know, it's going to be, I'll delete that. This is going to be, and the whole width of the damn thing is supposed to be, what, 20, 21, that's going to be, how is that, yeah, 18.42 is what they're calling it. I mean, how thick's this one again? Yeah, pretty darn close to the spec anyway. 18.5, so 18.5 on the base, and then what's the top one? 19. I was gonna say 20, you know. Just to give ourselves some margin. So from the centroid here, so we've got, you know, this is going to be 10 minus 2.54. And then this is going to be, going to be 10 plus 2.54. There we go. Okie doke. And that gives us a cutout for us to push the mount through, the screw hole through. And realistically, I don't know what the inset of this screw is supposed to be. You know, it's, I mean, maybe it's defined, probably is, but I don't see it in this document anyway. What the inset of this bit would be. But anywho, and we give ourselves a vertical thing because we want to be able to slide the card in on top of the chem connector, and the little hook will go through the hole, and then we can drop it down. So what we'll do now is put a, we'll do an extrusion on the face here to basically support the, actually what we could do, just so that we don't have to deal with, actually, yeah, so we don't have to deal with, we'll do this in post, not post. Because I want to print it at this angle, I don't want to have a piece coming out, because that would be an overhang. I don't really want that. So, yeah, because we printed an angle, you know, you put a little, you do the fins, and you don't need to print with generated supports. And so what that would like, if I don't need to print with generated supports, yeah, it's a little more efficient. So, I mean, I could put a single tower, like print, you know, tower here, but it would be nice to not need the travel. But either way, it's probably fine. It would be a flat surface. Well, we would angle it at whatever I had to rotate this at to fit it. So remember, if I do rotate it, like, not only do I have to slide it in to fit this in the print axis, it's Well, actually, I take that back. If I rotate it up like this, the actual like horizontal distance is less. Yeah, but the vertical increases. I did all my math wrong. Okay, what the heck? Okay, so it's hypotenuse, right? So if we did, what if you do 1, 1, and then it's root 2 over 2. So, or it's root 2 on for the 45, 45, 90 triangle, right? Is 1, 1, square root of 2 is the length of the hypotenuse, right? So if this was 200 millimeters, which it is, you would have to divide it by, not multiply, you divide it by the square root of 2. So it's, yeah, times root 2 over 2, sorry. So it'd be like 0.707, right? So this is 0.7, so it actually gets shorter, but then this gets also, but this is now contributing to length. So if this is, what did we call it? It's right now, I mean, if it's going to be 4U, it's going to be a good 1.75 times 4. Yeah, that's 7 times 25.4 millimeters per inch. Yeah, 177. 177 times square root 2 divided by 2. It's 125 plus 200 millimeters times square root 2 divided by 2. It's too big. Damn it. All right. So we got 256 millimeter, not 266 millimeter. Ah, crud. All right. So we can't print it at an angle. Might have to do it all. We might have to do the whole thing vertically. It's gonna suck. I mean, we don't have to rotate it 45 degrees. We can do like 50 degrees. If we did, we'll figure it out. We'll figure it out later. But anyhow, in order to deal with this thing, if we put a little bracket there so that the network card can screw into, we might just want to do it where we put a little mounting. We put 2 like mounting screws like into the face, and then we screw the mounting plug on after we print. So that we don't have to deal with printing supports. That would work fine. So we'll just leave this as is, because this will be for you, Tal, when we're done. I just didn't know how I want to install the hard drive cage yet. Yeah, we'll just so we're not surprised. Enclosure height 4 by 1.75 inches. So now we know. Now we know what it actually is. Enclosure height 1.77.8. Yeah, there we go. It is a 4U enclosure. Of no surprise to anyone. All right. Might just print this out of PLA tonight just to see sizing, form factors, and stuff. All right, so we've got an I/O cutout. We've got a PCIe cutout. Else we got? I mean, obviously we're not ready to print it or anything. But oh wow, I got pretty close to nicking the enclosure wall. Interesting. Okay, so 3mm PETG is not strong, but with cross bracing from the hard drive enclosure, it's probably fine. The idea is that we're going to stick. Well, hopefully we'll be able to fit 6 hard drives vertically somewhere in this space. We'll have to figure out how to do the drive cage mounting on the inside here without taking up all of the volume from, because there's going to be volume consumed by the cooling fan of the computer. We could just pull air through the hard drives. I mean, that'd be really, it'd just be come out really hot, but anyway, Overclock the HDDs. A whale. So... What? So then, I mean, obviously the next major thing to do is actually to... Here, let me hide the motherboard mock. Yeah, so that's the mounting holes are. So one of the next major things is just going to be figuring out where the hell to place a power supply. Because it's DC to DC unit. The motherboard's only so tall. Thinking of mounting it over the RAM, essentially. I figured a good place to put it. And then we got this thing's all DC to DC powered, so I gotta come up with a way of... Oh, there's an ant. That's not good. Anyway, ways of mounting stuff. Probably mount the JetKVM board on the wall over here. Mount the JetKVM over here. Capstone in here for the thing. Should probably measure. Oh, tomorrow I'll need to measure the height of the. Oh, kittens are gone again. Measure the height of the PCB, the motherboard with the fan, because I know we said 1U, but now we're going to be, might even need to just, millimeters might matter here. So, we got to, this is already at 4U. So, because there's going to be some height consumed by the cooling fan. The heat sink basically is the rear I/O shield. And the fan is just a little bit on top. I got one of those knocked to a 15 mil fans, so it's only 15 mil up from here. So hopefully that'll give us a little bit more space than we do our hard drive mount in here. We need to think about how we're going to do the hard drive mount. Probably I'm going to... Because there'll be a top in here, but they'll... I mean, because of this card, we can't exactly cross-brace it. Well, anyway, if I were to export this right now, how much PLA would it take to print out? I'm just curious. I don't want to do it. I want to do it, but I want to get some actual like bits, more important bits done first. I'll go back to the bamboo. If I were to delete that, come back and bring desktop, enclosure. Oh. Too close to extrusion area. There may be collisions when printing. You booger. Oh, come on. Auto laid over the boundary. I know it's basically the maximum. Give me the translate tool. That's a thing, right? Yeah, there we go. Too close to the extrusion zone. Where is the jump to? Yeah, where is this keep out volume? Oh, I'm trying to remember. What if we? Well, I mean, the idea was to print it face. If we're gonna do this, we're gonna print it face down. Too close to the extrusion area. Maybe collisions when printing. Where is the extrusion area? Where is this boundary? And not the external boundary, but the range. Oh, cool. Now it's happy, I think, right? Translate. Will it be happy? Oh. What extrusion area are we talking about? If I put it forward. Oh yeah, it's extrusion area. Oh, maybe it's where it's some... No, don't add a plate. Sorry. Arrange. There we go. I think that's the front bit. Where it parks the head if it needs to like purge or something. So that's probably what this white area is marked for, right? If I don't cover the white area. Okay, I see. It's this white zone right here. That white area is there to tell me where not to put this. Okay. Well, that makes a lot of sense. Also kind of annoying that it cuts out of my build volume, right? But whatever, I guess. Slice plate. How much PLA would it take? Huh, besides a shitload, 523 grams of PLA. Just a test print? Oof. If I wanted to test print the whole thing. That would be a lot. I don't want to do that right now. It'd take 7 whole hours to print. What if I had an 8mm nozzle? Well, how long would it take? 6 hours to print? Oh, interesting. Yeah, 7 hours 54. 7 hours 36 to print with 0.4mm nozzle. 7 hours 54 to print with a 0.6. What? Then 6 hours 29 to print with a 0.8. That's funny. Okay, sure. I'll dig it. I'll take it. Whatever. Alright. That's a lot of mass. I'm gonna need to probably buy some more PETG to print this. Alright, but yeah, okay. I dig it. So it weighs a whole pound. That I mean, half kilo. A little more than a half kilo. But all right. So right. All right. Well, either way, not going to print it as is. There's more stuff to do. So yeah. All right. I think that, let's see, what else can we do for the basic layout? If we figure, okay, so at least let's figure out what the hard drive cutout might look like. So we're looking at 3.5-inch drives, so it's 3.5 inches tall, right? So let's actually not actually cut into it. We'll use a drafting tool. So if we force this to be, 3.5 inches tall, 3.5 inches. Oh well, not. Delete. 3.5 inches. Just to give us some margin, we'll say we have a quarter of an. How tall will our mounting hardware be? Quarter of an inch would be 7-something millimeters, right? So yeah, let's say a quarter of an inch for mounting hardware. So let's just say it's gonna be 4 inches tall. So yeah, 100-something millimeter. And width-wise, we're gonna have a 3.5-inch hard drive. Height is 26.1 millimeters tall. So wait, 101.85 millimeters wide. Wait. Huh? Oh, the platters are 3.5 inches, not the geometry of the oh. Okay, 101.85 millimeters. So that's 3.5-inch drive width. Yeah, is a 4 inch because the platters are 3.5, not the actual size of the disc. Okay, not the size of the Sorry. What the heck? An earthquake? Big truck? Something? Okay, anyway, it's 4.5 inches, I guess. That makes life more annoying. Yeah, they won't fit. They don't fit. They don't fit vertically. Oh, crud. Alright. Well, that throws a wrench into my plan. Because I mean, I need gap for the. I need. I mean, technically, I only need 3 millimeters on the top. That's all I need. But I need air gap for the fans on the computer. There needs to be 15 millimeters here, and that'd mean they'd be bumping together, which would not work. Okay, this is intriguing. This is not great. Wow, my napkin math sucks. Okay. Who'd have thunk? So if they're 4 inches wide, that means how wide would this need to be? Well, overclock the PTG. Yeah. So ideally, ideally we would stick to the specifications, right? Yeah, but with this rack, I could make the computer wider than spec, but I would need to. I wouldn't be a great idea. I could make the computer wider than spec, but wider than the actual enclosure is allowed to be, just because I can fit things, but I don't want to do that. I mean, realistically, it'd be kind of difficult too. That really throws a wrench into my plans. Because I would love to make the motherboard or the mini-ITX case just a 2U enclosure, but I need space for this network card vertically. Because my original plan actually was to build my own riser card, my own hard riser, essentially, that would rotate the network card 90 degrees to the side. But, I mean, I know there's some of those on the market, but the reason that I wanted to build my own is that I wanted to build a bifurcating riser. Basically, give me an X8 slot, an X4 slot, and then one M.2. The M.2 would be for my my SATA device. And the M.2, well, realistically, I don't want the M.2. Realistically, I want, like, Slim SAS HD or Oculink. Well, I don't want Oculink, because despite what all of this stuff on the internet wants to think, Oculink sucks. Like, it's not... Like, yes, it is faster than Thunderbolt, like in the sense that you don't have a protocol overhead, but it sucks in the fact that the connectors are shit. They're fragile, they break easily. The cables fray internally, like the how much you can bend the cables has a very tight specification. Like we were using them for a product, not for a product, but we were using them for an internal thing at work, and we literally probably like 9 months into the design process on that, we got rid of them all because they sucked so bad. Like the moment that cables started turning and putting any sort of flex on the connector, it just lose connection, or the connection would be intermittent, and you would get PCIe corruption. Like, it'd be correctable, but like you'd get corruption randomly and throw off all your latency number. Oh, it's so bad. I hate Oculink. It's so bad. You should everything should have gone to mini SAS HD, because it's so much better of a connector, and it's not much bigger. It's not much larger of a footprint. It's taller but thinner. And there's also spec on SlimSAS HD to go to 8 lanes as well. But either way, just sorry, rant over. But anyway, so I wanted to build a custom hard riser with 2 slots, one dual, essentially one dual slot unit for or cutout for an Intel NVIDIA, like a Quadro SFF, like a half height, and then I'd have another X4 slot. I'd have an X8 for the GPU. I'd have an X4 for the network card, because even though this network card is an X8 card, it only really needs like X2, it only needs like X4 or X2 really, because it's a Gen 3 card. So on an X4 link, you get 4 gigabytes a second each way. It's only got 2 10 gigabit NICs on it, and even though the Ethernet is full duplex, 10G SFP plus is full duplex. You can it's only 20 gigabit each way essentially. It's gonna be 2 10 gig out, 2 10 gig in, and an X4 you can do that over that's more capacity than a Gen 3, because Gen 3 is only 8 gigabits a lane, so like 10 gigabits. But an X4 link fully saturated, so I only need X4. So I was going to do an X4 slot for a network card, X8 for a GPU, and then like SlimSAS HD or Oculink to take out to an external enclosure where I was going to embed my M.2 SATA controller in there, because I don't have the money to make a deal with ASMedia or whoever in order to make my own custom SATA controller card, which I'd love to do. I have sufficient skill to do it. I'm not hiring a lawyer so I can sign a contract with them and then not actually be able to talk about building it. So either way, so this was hopefully kind of my fallback, making this for you thing with these hard drives in here. But if it's too large, then because clearly I need, how much space do I actually need? So the card is 0.8, so that's if we take our 8 point, how wide was our desk pi? We got 8.75 inches inside here, minus, so that's 8 inches. And then two 3.5 inch drives, even if they're pressed right up against each other, no mounting hardware, 8 inches. So it's already not going to fit. Okay. We might just have to go to 5U. not before. We might have to just go to 5U. Might have to print out a 2U. I hate that so much. Maybe I can embed one of my switches into this case, just so I can make use of the volume and not feel bad about wasting all of this volume right here. But because if we shrink this back down to sorry, where was it? It's height. Yes, we go back to 3U. And honestly, I could cheat, and in the bottom slot of the rack, I could kind of steal a third of a U off the bottom. Because I don't want to waste all this, because the fan's only 15 millimeters above here, and then you need to give it another 30 millimeters so it has enough of an air gap. Maybe we do even more. I mean, you could. But I just don't want to waste that vertical space. Put a bunch of capstone jacks in there. Put my switchboard in there. My capstone jacks for my network switches in there. We could always do that. But well, we have hit I think I'm gonna call it for tonight for the stream. We just crossed 4 hours of stream time, and it's almost 11. So I'm gonna do a think on this for the next next couple of days. Figure out what I want to do. We may continue with the modeling of this like on stream. See my poll on the posts on my channel to trying to decide what to do as my next on stream like thing, because obviously I'm mostly focused on robotics. This is kind of a side project that I have to make things a little better for my storage stuff, but and it's 3D modeling. It's cool. We're making stuff. So but I also know that that's not necessarily my core audience. They all all my stuff has been about robotics. So I posted a poll asking about what people want to do for the next would be interested in watching for the next project. So I got a couple things up there. If you don't like the options, just leave a comment down below. Basically the thought is that one option would be build a robot from scratch using robot operating system that can navigate around like my apartment. Basically it'd be like a SLAM-based, LiDAR-based robot. We'd build it from scratch, including the electronics. I mean, obviously not the LiDAR, but we build a board, we put it together, we'd 3D print we 3D model the chassis, and set up ROS. Another option would be porting ROS or taking an existing open source robot and bringing ROS to it. So if you can see in the back corner, there's the robot with the arm. It's a Lake Kiwi mobile manipulator with a Hugging Face SOR 101. So we could bring ROS to that. Another option is building. So it turns out the Pulse can only have 4 options, but I really wish there was a 5th option. So I have 2 options about building a GPS guided robot. Now I've already did that, as a personal project over the last couple of years, but I never really documented it anywhere. So that's the GPS robot is what we were hacking on with Robo Magellan, with the IMU, the trying to do the whole Chibi OS thing. People didn't really care, but basically there's two building one of those GPS robots from scratch so that everybody can follow along with where it actually is, and not just be some existing robot I have that I'm hacking on that nobody else has because it's a custom thing. And another option would be do the GPS. So it's basically build a GPS guided robot from scratch, either with ROS or with a custom software stack. Because my current robot uses a custom software stack. Make a vid giving all your robots armaments. I guess we could automate one of those the electric powered Nerf cannons, because the air powered ones are a pain in the ass to automate. Yeah, and then so basically the 2 options be GPS guided robot, either with or without ROS, either with custom stack or with ROS 2. And then the 5th option would be, again, robot from scratch, but rather than doing a ROS navigation thing, we would just do it as like a tablebot, like a Homebrew Robotics Club like tablebot challenge, where it's build a robot, it can run around on a table, find a block, push it off. We do something more advanced, like put Aruco markers on it so that a phone would be able to locate the thing on the table just by like scanning the table. But I did buy a really cheap Mechanim drive kit. It was like $15 and four motors, 4 Mechanim drive wheels. It was actually hilariously cheap. I mean, the quality is utter garbage, but $15. Like, you can't really ask for much. Like I've spent that's a hamburger these days. Either way, see the poll, vote on what you'd like to see me work on next. So we might do one more stream about this if I can simplify it a little more. But Still trying to think of what to do, because the original plan fits. Actually, the reason I was talking about the spacing of the riser thing, like that was doing the math to figure out the exact dimensions of where these holes were. Yeah, that was one of the big ones. But in addition to that, it was I needed to be able to build a riser card, and it was like, okay, I can build the riser, but then there's the question about how to do the Oculink or the mini SAS HD, and it was like, okay, well, sorry, it's not mini, it's Slim SAS HD. That's the name of the connector, Slim SAS HD. So it was like either I do Slim SAS or I need to make the hard riser. I was trying to think of what the design was going to look like, but then it was like, oh well, how do what is all the mechanical spacing on this thing? And I was letting molehills, was making mountains out of molehills, but again, I'd have to design the riser. That might be a fun video. The riser was part of it, because I've got 8U in this thing, right? So, and the reason I bought the 8U rack and not the 12U rack was I wanted this thing to fit inside my entertainment center. And I believe if I take the handles off, I think I could just barely squeeze the 8U rack into my entertainment center. So, the thought was, so that's why I went with the 8U rack, but I was really hoping to keep the compute stuff to 4U, because I could put the computer in, that'd take 2U, I put the hard drives in, that'd take another 2U. I have a network switch, I have a 10 gig network switch, that takes up a whole U, so that leaves me with 3 left. And then I need, I've got my router, which is a tiny little thing, I'm not even really worried about it. And then I wanted to put in a 2.5 gigabit switch. So maybe the router and the 2.5 gig switch could sit side by side in the rack. It might fit. So maybe that's another use. That's 6U. The initial design, I had a power shelf, because this whole thing is going to be DC powered. So I've got one of these like 48 volt Meanwell supplies. So his original design was going to have a power shelf. So that'd be 7U. That only leaves me with 1. And I was and then I was thinking about putting it. I need somewhere to put all the network capstone jacks that run into stuff in my apartment. So that was going to be the 8U, and it was going to be full. No more room for expansion. So yeah, I was going to take the power shelf out. It leaves me with 1 extra U, but I really, really wanted to try to keep the computer and the hard drives into 4U. But maybe we don't. Maybe we don't for now. Until I can build the riser, then we tweak the case a little bit. But yeah, so I might do another stream on this. I might just bite the bullet and go with 5U for all of the setup. I mean, that'd be a little lame. But if we do 5U, what I will do is at least make mounting. Okay, so what I will do is if I do the 5U enclosure, make the computer 3U and then make a separate hard drive enclosure that's 2U. What I'll do is, or how do I want to explain this? What I would do is, I'll embed the capstone jacks for all the Ethernet into this case. So essentially, I'll have like on this side, maybe there'll be a little would be blocked off, for the network card to mount in, but it'd almost be internally there'd be space above it so I can bring in the network capstones. And the capstone jack is basically it's a Ethernet receptacle rather that turns into a cable on the other side that goes somewhere. So I bring in all of the cables from stuff in my apartment, mostly my entertainment center. Because really, outside of the NAS, there's a Wi-Fi switch. That's about it. The Wi-Fi. There's 2 Wi-Fi routers. One's my personal. One's my special work Meraki VPN router thing. And then Jesus. But yeah, put the network capstones along the top. Just so we can make efficient use of this space. That would also give me a lot of room to shove in that the JetKVM. I'd have so much space in here. It's just we're playing Tetris with computer equipment, basically. I, mm. But yeah. Oh yeah, and I also didn't even account for the vertical. Oops. I also still haven't even accounted for the vertical size of the top of the case yet. Okay. Well, we'll have to do that. It's basically going to be the rest of this. And it also needs to be removable, so I can actually put shit into this box. Okay. Yeah. Huh. I got some thinking to do on this. Maybe we'll pick this back up on Tuesday, and I'll wait another week to start some other project. The thing is that like I've got the next Robotics Club challenge, right? Is at the end of September, so I'd like to start one of the robot projects before then, right? Anywho, so yeah, maybe we'll pick this up on Tuesday again. Do one more day on it. Do one more week on it. But other than that, I think that's where we'll leave it for tonight. I'll do some thinking. And yeah. Well, so again, vote on the poll. Thanks everyone for watching, and I'm gonna twiddle my thumbs here for a little bit just to make sure that I end the stream after I finish talking. And have a good night, everyone.